Hi there. I recently went to go visit a very good friend of mine and fellow radio enthusiast, Dan Schultz. Now, Dan has got a lot of really nice radios kicking around, and when I was at his place, I was on my way out and spotted this HQ-120 off to the side and was like, wow, that's a really cool looking receiver. So I looked over and I said, Dan, you want to part with that? And he says, after a bit of talking to him for a while, he said, sure. So I promised him I would do a restoration video on this, and that's what I'm doing right now. So I hope all you people that are watching this enjoy this and enjoy following along. So I'm going to do a complete electrical resto on this, basically take out all the caps that need to be replaced. And that, stands for really the electrolytics and all the paper caps, if there are any of that in this. I haven't even looked in this. What you're seeing right now is what I've seen. I basically brought this thing home and it's sitting right here, and this is all I know. So what you're seeing is what I know, and we'll go through this piece by piece together and we'll discover everything that needs to be done and go through a complete electrical restoration and make this thing come back to its former glory from, say, 1938 or 1939. Now, this is a really good example of a Hammarlund radio. This HQ-120 is, the face is, almost no marring or no scratching on it at all. All the knobs are original. The meters haven't oranged or yellowed, and the dials look really nice. Even the case is in very good condition. Could use a bit of cleaning up, but, that's pretty much where it's at for this. So this is a general coverage shortwave receiver for those of you that may have stumbled across this video or don't know what a shortwave radio is. And what this thing does, kind of in a nutshell, is it receives a whole bunch of different frequencies. It's like a broadband receiver. It allows you to look at an entire spectrum of frequencies. You can go, right from about the bottom end of the broadcast band right up to about 31 megahertz, which is pretty high. So that's, looking at the broadcast band. If you were to look at, say, your AM and FM radio, okay, you have the AM radio down here, which is 550 kilohertz to, say, 1600, and then way up here, you've got 88 megahertz to 108 megahertz, and this whole area here, you're not seeing. So what happens is this receiver basically goes to about here, all right, to about 31 megahertz, and then there's just a little gap that you're not getting in here, and then there's the FM broadcast band again. So it really looks at just a large spectrum of frequencies. And now these short waves, so-called, what they do is they work on the principle, like if you were to, say, go down to your local lake and pick up a rock and skip it on the water, it kind of skips and bounces on the water. Well, it's the same thing with radio signals. What radio signals do is, say, Japan is transmitting a radio signal, it's going up into the atmosphere, it's hitting the upper atmosphere. There are actual layers, and I won't get into all that, but we'll just call it the upper atmosphere. It's going up there and it's bouncing and coming back down over here in North America. And what we can do is we can hear signals from Japan, we can hear signals from Australia, lots of signals from Asia, some from Russia. They're all over the world you can listen to, and there is no internet connection, there is no cable connection, there's really no anything. All there is an antenna wire that comes off the back of the set, and it's usually called just a random length antenna. You can cut them to resonance, which means that you're tuning them for a certain area of the band, and then it'll really hear good in that one particular part. Or you can just run a random wire out, which is usually about, I like to say, about 100 feet or so. So you run a piece of coax off the back or whatever, and then outside your house you just run a 100-foot piece of wire, and you listen to signals from all over the world on just this box here without any connections to anything else. And that's really what a shortwave receiver does, a general coverage receiver. Now, there's kind of a sport behind this. A lot of people like to collect receivers, like myself, and compare them and listen to them and all that kind of stuff. And you can listen to ham broadcasts and all sorts of things on these things too. So they come in handy for myself. And so that's really what this is in a nutshell. So what we're going to do is go through this thing, and as I say, just step by step go through it and completely restore it, and bring it back to its former glory. So let's get into it, and I'll pop the lid next and we'll take a look inside and see what they've done, see if there's any tubes inside of it or what they've done to this receiver, and we'll go through step by step and bring this thing back to itself again. Here we are looking at the lid of the Hammarlund radio. So how you get into this radio is you just stick your finger in here and kind of pop this open. Put my hand here so it doesn't go flying, and like so. And then you can see there's a little clip here which just clips to the front of the radio here. And we're inside. Much easier to get into than some of the solid state stuff, huh? So here we have all the tubes laid out inside this thing. And we immediately notice that there's two tubes missing, one here and one here. So this 6Z7 here has got a phenolic tube socket, and the 6K8, which sits over here, which is the mixer tube, has a porcelain tube socket. And you're probably wondering, well, what's the difference in the tube sockets? Well, the reason that they have a porcelain socket on this side is because you need an actual tube socket that's really sturdy, that where the contraction and expansion of this tube socket is kind of held under control. Whereas if you have a phenolic socket on this side here, they move around with heat like crazy. And what happens is that, you know, sometimes just you wouldn't even think of this, but the actual wiring that's connected to those tube socket pins and the actual tube pins are moving around a little bit with expansion and contraction when the tube is heating up and cooling down. Now that expansion and contraction changes the capacitance between the pins of the tube. It changes the capacitance in the wiring and the chassis and everything. So when the capacitance changes, that also causes dial drift. So what they've done is they've got a porcelain tube socket over here, and of course it's more controlled. It's a little bit more rigid than a phenolic tube socket. So by having a porcelain tube socket, they're controlling the drift that way by having a more sturdy structure holding that vacuum tube. So that's the reason that there's a porcelain socket there and a phenolic socket on this side, because you don't really need to have porcelain sockets everywhere. So they're just looking at drift. And it's the same thing. The main tuning condensers are under here, and they all have a porcelain structure on them. And that, of course, is part of drift compensation, stopping the radio from actually drifting too bad. You got to keep in mind when you have this radio off for a day, it's at room temperature, right? It's nice and cool. But with this lid closed like this, just using the vents on the radio itself, you have all of these tubes that are just blazing hot in here, glowing inside this unit, making this go from room temperature to as hot as the blazes of Hades. So by having this small vents on the back allows a little bit of ventilation in here, but you also have a very, very vast temperature range where it's going from room temperature to its actual operating temperature, and that of course incurs drift. So all these old radios, you always see a little bit of drift, so they always tell you, warm the radio up for a while before you use it. And that's just standard practice with any vacuum tube receiver. They, as I say, there's a very, very large temperature variation. You'll notice that in the more modern receivers that use transistors or ICs, that there's not very much drift in them, and that's because there isn't such a large temperature variation. It has nothing to do with the actual structure of the transistor itself or anything like that. It's just the fact that it's not really going from room temperature to as hot as your kitchen oven. So this is the reason that people say, oh, tube radios drift. Well, no, actually, if you let them warm up and stabilize, they're actually very, very stable. And the designers of this Hammarlund radio took all of that into consideration when they were putting this thing together. So this is the mixer tube here, and you can see there's a rubber wire on the actual grid cap, and the rubber wire here is just as crispy as pie crust. So we're going to go inside this thing and replace that wiring. You can see somebody is very hokily, this is a real hack job, mounted a speaker onto the back. Doesn't look like they've done too much damage. It's just, they've mounted it to the back here, and they're firing it, out this way, which is kind of useless because I'm listening on this side of the radio. So we'll get rid of this and use a proper communications speaker in that spot. A bunch of really interesting things that are kind of overlooked in the design of these radios, and one of them is they use a 5V4 as a rectifier tube in here, okay? And we can see the plate structure here, and we can see the little coily white filaments there, and then the actual indirectly heated cathode. Well, what's interesting about this tube is that coily filament is directly connected to that cathode. So in effect, a heater to cathode short, really, if you think about it, because it's part of the cathode surface. Now you're probably thinking to yourself, why the heck would they design a tube like that when they can just use a 5U4 and or a 5R4, and the filament itself is actually the cathode? They've actually tied the filament itself to an isolated indirectly heated cathode. Kind of makes no sense, right? Well, there's a reason for that, and it's called controlled warm-up time. So what happens is when you first turn these radios on, this transformer has no load on it, so the B+, the AC side or the plate side of this tube, goes really high in voltage, okay, because there's no load on it. So when this is going really high, if you have, say, a 5R4 in here, which is a directly heated tube instead of this, right? What happens is you turn the switch on the radio. Now it's doing its rectification, and that tube is full in. It's putting out all the voltage that this thing can, supply, and none of the other tubes in this receiver have warmed up at this point, so the voltage surge is really high, and then when all the rest of the tubes warm up, it drags it down slowly to below really the safe ratings of the capacitors. So by having a controlled warm-up time, this tube warms up as well as its fellow tubes inside of here, and you don't get that really high surge voltage that's kind of destructive to the filter capacitors and such. So it just makes it a little bit more reliable. And that's why they've done that. That's why they've designed the tubes like this. So this has got a 5V4 in here just to control the warm-up time so that we don't get such a high surge voltage. We can see the 6V6 is an audio output tube right here. And if you look at the plate structure inside of this, I've never really quite seen a plate structure inside a 6V6 so big. Like, look at that. That's a really large plate structure in there. I've got lots of 6V6s, but none that look like that. So, yes, this would probably love to find its way into some guy's guitar amplifier, I'm sure. It's a very interesting looking 6V6, made by Raytheon. So, there's that. Here we have another tube here, which looks like it has a shielded lead running up to the grid. The grid cap. This has got two triodes inside of it. We can see right through the ST style glass here. So this is a 6F8. And what the 6F8 looks to be doing on the schematic here, if we look at the 6F8 here, it looks like it's doing detection and amplification here. So we have a 6Z7, that's the tube that's missing, and that looks like that's the noise limiter tube. You can see the limiter, and it says on and off, and it connects and disconnects the cathodes of this tube. So this can't really be doing any detection at that point. So the detection is obviously occurring in the 6F8, and then of course the amplification is occurring here. So if we follow the grid line out, you see it goes to the audio gain control, and then it runs, into the plate of this tube here. And then we can also see on this particular side here, we have the grid and the plate tied together, which usually indicates that they're just using it as a diode, right? And that's acting as the detector on the other side. So that runs off to this line, which of course runs up to the last IF transformer, which makes sense. We have down here the BFO circuit. The BFO circuit is the beat frequency oscillator. So this is what you use to insert that small carrier to create a heterodyne tone, and that tone allows you to listen to CW. So if you don't have a BFO in your radio and you tune into CW on the shortwave band, it'll sound like static turning on off and on. It'll kind of go if you're listening to CQ and Morse code. Whereas if you have this and you turn this on, it'll add a tone. So it'll go it'll actually put the tone in there, whereas before you would be listening to the actual static. This is the output tube here that we just looked at. The 6SF5, which is over here and kind of hiding, looks like some sort of a meter control circuit. It's running right up to the meter amplifier, some form of a control circuit. And we can see over here, this is the input RF, which is a 6S7. It goes from there into the 6K8 mixer and then through the IF chain and out the last IF amplifier, which is a 6F6, which is another really interesting choice for an IF amplifier. So what happens is the chain really, the antenna, basically it comes into here, it goes this way around, and then comes back out over here, and then it goes from this transformer over into the detection over here, and then runs out the audio output tube. This guy is a voltage regulator tube, and they normally glow purple. So if you see one of these tubes in there, it's a VR150, and it's glowing purple. It's not bad. It's not gassy. It's actually supposed to. This tube has a gas inside of it, and it's designed to regulate voltage at 150 volts, hence VR150, voltage regulator 150. And that's nicely stamped into the socket here also. VR150 down there. When you're pulling these out, you got to be careful. Just kind of rock them and gently pull them out. If you bend them too much, you'll break the indexing off in here, and you don't want to do that, and then you'll have a real hard time trying to align it to the right pins. So what I do is this one is just fitting in perfectly here, but if you don't, what I normally do is I put one finger on the top and you just rotate it like so, and then it just falls in. So those are pretty easy to put back in, these octal tubes. They also have a tube, and a lot of other radios, Philcos were really known for them. They're called loctal tubes, and they actually have a lock on them, a little lock on the base with small pins. And those tubes also have this kind of an index in the center, but they also have a little clip on the bottom which holds them in. And they were widely used in automotive radios because they were a pretty sturdy tube to have. But these are octals, sorry, not loctals. So that's pretty much how this thing works inside here. You know, there's a nice potted transformer down here. Here are the dial lights right here and here, and there's a dial light in the meter. A lot of people were crazy and they pushed this thing right up to the meter and burnt, you know, the front part of the meter. So this one is looking like it's pretty good still. I always like to use a small, shallow, kind of a rounded head bulb. A lot of them use the long kind of like 47 style bulb. I like to use the little rounded head guys so that just in case you actually do bump it or something, it won't burn the face of the meter. And sometimes I even get really crazy and I will LED light these things, just the actual meter itself, so that there is no chance of that happening. There's, you know, massive space between this bulb and the actual dial here, so you're not going to ever burn that. But this is a kind of a sensitive little area here. So depending on it, this one here I'll probably just put a dial light back in and light the meter up that way. Here we are on the underside of this Hammarlund HQ-120. This was much easier to get into than I figured. I didn't have to remove all the screws on the face or anything. All I had to do was tip it up and remove the screws on the bottom panel, and we're inside. A lot of these older radios, you got to remove the screws around the face and pull them out of the cabinet, and I just took that for granted. I'd probably have to do that with this too, so I'm kind of thankful it turned out like this. This is pretty easy to service. And somebody has taken advantage of that easy to service, and I'll show you here right shortly what I'm talking about. We can see on the underside here that all of these pink capacitors have been changed at one time. They're tiny chief capacitors, and they were replacing these waxies. Somebody removed most of these things and put all these pink ones in. Well, that does us no good today because all of these pink ones are bad also. They're paper caps and they leak like crazy, so they're no better than the waxies. So the waxies have got to come out, and all the pink caps that you see in here, they all got to get removed. This guy is just kind of floating in midair. It's a filter cap, so that's got to come out. And there's two down here that are probably going to be bad also. And well, I know these are bad, and I'll show you that too here in just a second. We can see that they've botched this section up here quite a bit. You know, there's resistors just floating in midair, and wires attached to them here, there, and everywhere. There's another floating thing down in here where the wires have just kind of all come up to one point. They've kind of, you know, attached them all and just they're hanging in midair like that and soldered them together. So that all really has to go. So I don't know what they've done in this section here. It looks like they've tried to modify it. There's it's marked 6H6 here, but there is no 6H6 within this chassis. There's a cover on the bottom of the BFO here that's missing, so I'll have to make something up here. And basically that's just to stop the injection level from being too high. And they put a can on it to shield it to you know, keep the BFO injection, you know, not crazy. So I'll have to make something up for that. We can see, as I say, a lot of different resistors. A lot of resistors have been replaced. Here's one here, one here. This is not factory. You know, they're all over the place. But just by looking at this choke down here, I can see that some of the hair-like wires on it are, you know, kind of coming off. So I don't know if this choke is open or not. I'll have to check that. And yeah, you know, this is really kind of an extensive repair. So this will take me a little bit, but I'll go through step by step, and we'll get this thing working again. At this point here, I might just, as I say, change all the caps, and well, I will change every cap aside from the micas, and I may even resistor this entire radio. I might have to wire a whole lot of it too. It's looking like it might need it. You can see some caps or something here has blown up at one time. We can see this dark spot over here, and it looks like something is, you know, exploded pretty good in that corner. Batteries in my flashlight are kind of going haywire. And you see, it's, you know, it's got a lot of issues. There's some other blue-looking cap up in the corner here. It's kind of, you know, probably going to be bad also. Whether it is or whether it isn't, it's out of there. So now, when I tell you that somebody took advantage of this bottom panel here, the bottom panel, let's grab it. Fits, you know, on the bottom like so, and then you got to remove all the screws all the way around, right? Somebody's even wrote bottom front. They've been in here so much that I guess they want to, you know, mark it so they get the panel on the right way. If we look at the trimmer caps here on the coils, see these trimmer caps? They're almost all different. This one's different from these three, and then these two are different again. And then we look down here and there's one that's been replaced down here also. Now, usually when you see this inside a radio like this, what this means is that somebody's done a lot of screwdrivering because they can't keep this thing stable and they can't keep it on frequency. Maybe the dial's drifting a lot. So what they've done is they've screwdrivered it so much that they've wrecked the trimmer caps and they've replaced a bunch of them in here. And the reason that this happens is because these old waxies that are originally in here, and now even these red guys too, they would act just like the waxies. What happens is over time they decay inside and they start to leak electrically. Now when I say that they're leaking, I'm not talking like a physical substance. They're not leaking oil or goo or electrolyte or anything like that. They electrically leak. So what happens with these caps is they're only supposed to pass AC, alternating current. And what happens is they start to leak and they start to pass DC through them. And when they pass DC, they're effectively turning into resistors. And when they do that, they drag other stages down in the radio and cause resistors to get hot. They'll burn out IF transformers. They do all sorts of things when these things go haywire. So what was probably happening at the point why these got screwdrivered so much is that somebody didn't replace any waxies in here at one time, or they did, and these guys are starting to go bad. And it kept drifting off frequency, or the oscillators kept moving. So what they did is they probably kept screwdrivering it without trying to figure out the problem, and then wrecked all the trimmer caps. And that's a common thing within these old radios when people get in here and they don't know what they're doing. So what's going to happen is I'll check the values of these and make sure they're somewhat close. If not, I will replace these trimmers also. And these are usually really good. These are got usually some sort of a mica in here between them. This one here is almost wide open. Look at that. So they usually have some form of mica in there, and a compression style trimmer capacitor, right? So we'll go in and I'll probably leave some in and replace the ones that need it. These look like they're really badly tarnished, and it's looking not very nice there. So we'll have to get in there and see what's going on with those guys too. So what I'll do is I'll remove the camera off the tripod here when I come back, and we'll test some of these caps, and I'll give you an idea of what confuses a lot of maybe newbie techs and or guys that really don't work on tube equipment. So when I come back, we'll look into that. Okay, so here's a closer shot of some of the electrolytics. Now if you look under here, right in this far back corner right here, you can see this cap here has actually kind of exploded and sprayed some of its internal goop on this wire here. I can pick it off with my finger. You see that? Came right off there. And these are all pretty much ready to do that. This guy here is, as I say, floating in midair. And take a closer look at those ugly trimmers in there. You can see how ugly those guys are. Those are the waxies there, and these are all the tiny chiefs that have got to go. There's even ones hiding way down in here. So I've got to get down in there and clean them all up. And maybe I can get closer to this wiring rat's nest here and give you an idea. See here how these are just floating in midair, and there's another one that's just floating in midair here. Look at that ugliness. Yikes. See, it says 6H6 on the chassis here. There's no 6H6 in this radio, so somebody's tried to modify this. There's that hideously long stripped piece of wire here. Runs right up to the switch. And, black tape down in here. Look at this. It's got a little bit of work to be done here. If I look down in here, maybe I can get a shot of that snapped off screw. Right down in there, you can see it right down on the bottom there. So there's quite a bit of mumbo jumbo in this thing that needs to be cleaned up. All these resistors and caps that are hanging out inside here have all got to go. You see all these guys lined up here. And down in here, same thing. So that's what's going on right now. So I've got my capacitor tester on over here, and what I'm going to do is open up the leads on this guy right here, and so I'll leave this attached to the frame here. I'll connect the negative of my capacitor tester here, and this end will be open. I'll have the cap hanging out, kind of like this one here is just kind of hanging off, and we'll test this cap. And we'll look at it for leakage on this capacitance tester here. and see what's going on. So I'll do that right when I come back here. Okay, let's open up this tiny chief capacitor here from its circuit and test it. What we'll do is we'll desolder it from the socket so that no resistors or anything else loads the circuit. So basically this is just open right now. And we can see it's tied to the chassis. That's fine, because the chassis is isolated from everything. We'll just use this as the negative side for the leakage tester, and I'll tie one side of the gen rad to here. Okay, so we can see that it's rated at 0.05 microfarad. It's a 400 volt rated cap. Okay, and I'll put that on here and here. And we'll scoot over to the gen rad. Alright. So I'll hit test here. Okay, so we're 74.620 nanofarad. So what that means in microfarad is that's 0.07462. So if we test this on another tester, like my DLM-240, which I'll show you in a minute, it should read 0.075 is what it should read on a normal, like a smaller capacitance tester. So we'll come back here, and we'll do that right now. I'll remove this here. I'll turn my DLM-240 on. I'll clip this negative to here. And we'll clip this to here. And there you go, 0.075 microfarad. So that's kind of normal for these old caps. They're around that area. They move around. And of course, we do know that these old caps leak a little bit too inside. And the fact that they're leaking means that it takes a little bit more time for the circuit to charge the actual capacitor and measure the time. So it's going to look a little bit higher. All right, so that's 0.075 mics, and this is a 0.05. Now, most people would think that that's okay. All right, because it's reading capacitance and all. So now what I'm going to do is I'm going to hook up my leakage tester the same way, and we'll focus on the leakage tester, okay? This is a very important test for vacuum tubes, and this puts a lot of voltage across these caps. So if you're ever using a leakage tester, you got to be very, very careful. You don't ever want to touch this while you're testing, because there'll be 500 volts in some cases on this one lead. So if you ever do use these, you got to be very careful and make sure your leads are shielded, and of course you're doing this all at your own risk. So that's the way it goes with old vacuum tube stuff. There's a lot of voltage inside. So this is a leakage tester. And what it does is it applies voltage across the capacitor here, okay? So we'll start out at 6 volts, and we'll test it at 6. If that eye opens, it's not leaking at 6 volts. So it's not leaking at 6 volts. Let's go to 20. See how it's not fully opening? It's already starting to leak pretty bad at 20 volts. Now that capacitor is rated to be fine up to 400 volts. And of course at 100 the eye won't even open, as we can see already, we know that. So that's leaking, completely leaking. That's a resistor starting at 20 volts or around there, even earlier, and at 100 volts it's definitely a resistor. So we know that this tiny chief has definitely got some issues, and they all need to go. Like all of these capacitors need to, you know, be removed out of here. Now if we do the same test across, you know, a newer style capacitor, this one here is 473, all right, let's see if we can get a focus on that there. So that's 0.047. Let me put my finger here, maybe it'll focus on my finger. Just too close. There we go, 473, okay, at 630 volts. All right, this is a newer polypropylene capacitor. So what we'll do is we'll test it on the gen rad. So I'll focus back up on the gen rad here. And I can't see in the screen here, so you can see this here. I'm hooking it up, and we'll hit test. And that's 0.0467, so you can say that's pretty much right on 0.047 microfarad. And we'll test it on the DLM-240. I'll just hook it up to the DLM-240 right now. And you can see here that it's 0.047 right on the nose. That's a newer cap. So we'll go back over here and look at it on the leakage tester. All right. In fact, how about let's do this to make the test really good. Let's solder it to the chassis. I noticed somebody put a little solder blob here on the corner of the chassis. So we'll just solder it to the chassis and test it the same way we were testing the other caps. So it has a bit of solder on it. Okay. So now this is basically testing this exactly the same way that we're testing the other caps. And as you can see, it'll still read the same this way. It's just doing this just to make the test exactly the same. 0.047 right there. Okay. Now we'll do the leakage test. I'll tie this to the chassis again and put this to here. Okay. All right. So we'll go down to 6 volts. You see it's absolutely fine. Go up to 100. Absolutely fine. The reason you see the eye opening slowly is because it's charging the capacitor, and then when I let go of this switch, it discharges the capacitor. Some of the other capacitor testers don't do this, and you got to be very careful with those testers. The Heathkit IT11 isn't spring-loaded. They may have corrected that in their future models. That's a Heathkit IT11 right under there. This guy up here, and this switch, as you can see, it stays in the leakage. So if you disconnect the capacitor at that point, it's fully charged. It won't automatically discharge it. They may have fixed that in the future. I'm not sure, but this one is not spring-loaded. So anyways, back to our test here. So we'll go right up to 500 volts. So we'll put 500 across this cap. It's rated for 630. We'll press the test. Look at that. Absolutely no problems. That capacitor is very good. And this is a very, very sensitive capacitor tester. So if there's anything haywire with that cap, that eye will not open. So we can see that these capacitors, these new polys, are really good capacitors. Now I'm also very fond of these disc type. These guys here work very good for RF bypassing. And I will probably use a whole bunch of these particular caps. These are 0.02s and I have 0.01s. And I'll use these in here for RF bypassing. They work very well at RF frequencies and drag the RF to ground really nicely. So you'll notice that Hammarlund used a lot of these in their SP600s. And even in the HQ-140, they had all disc caps, and to this day, they're still fine. You don't have to recap those. The only thing that needs to go is the electrolytics. So these guys are all paper, and they all need to go. So let's look at here really quickly an old waxy before we do anything here. And I'll tell you a couple things about waxy capacitors here also. So these guys here are almost always faulty. Whenever you see these in any radio, it's 100% out. These have got to go. And to tell you the truth, any Tiny Chief cap you see, they've got to go too, because these are paper caps also. So you'll see that they've got a line at one end here. All right, see that line? Now that line denotes outside foil. That's all that line means. So what happens is this lead here runs to the outside foil, the foil that's closest to the outer shell of the capacitor here. So technically, like, this is all shielded right up to this point, and then this one here would be the inside layer foil. So this end of the capacitor always goes to the lower impedance point of the circuit. So if you were to be using these for RF bypassing, this end always goes towards ground. And you can see they've even helped you out on this one. This is marked ground at this end here. And you can see they don't mark ground on a lot of them because this really, wax caps aren't polar. Electrolytic capacitors are polar 100%. But these guys here, that's the only reason that line there, it's to help you get less hum and less interference in your circuit. So this guy here will always tie to the chassis side if they're RF bypassing caps. So what I'll do is I'll test this waxy here. We've still got the negative lead of the leakage tester here tied to the chassis, and this end is tied to the chassis. So what we'll do is we'll hook our leakage tester to this guy here. Now this is the same company of capacitor, and basically this is, what's inside here is what's inside here. This guy's rated a little bit higher voltage. You can see it's 0.05 at 500 volts. It's made by CD, just like all the other capacitors are. And we'll check this one out on the meter. Okay. So here we go. We'll start off at 6 volts again. All right, not too bad at 6 volts. Look at 20. Same kind of idea. It's opening a little bit, but not fully. So this one isn't leaking as bad at 20 volts, but it is leaking. And of course at 100, we're gonna, pretty much see closed eye here. So we can tell that that's really bad. This fella's leaking real bad. So it's the same kind of idea as the other pink style capacitor, the Tiny Chief. And what we'll do is I'll just hook up the DLM 240 here again. And we'll compare the measurements of that cap, okay? So ground here, and we'll go up to here. And we can see it's almost exactly the same reading as the other capacitor. Well, they're made by the same company, and they're basically the same cap. One's just in a molded shell, and one is in a waxy and a cardboard kind of shell. So we can kind of tell the paper inside is breaking down between the foil. It's probably going acidic, and it's definitely leaking DC across. We can tell it's taking a lot longer to charge this capacitor because the capacitance rating is up, just like on the pink guy. So we know for sure that all of those capacitors are bad. So all of the pink caps that you see within this chassis, all hiding under here, and that blue guy up there, and all down through here, and these electrolytics are bad too. There was a very large electrolytic originally strapped to this point here, and it was, in here a big cylinder, and somebody's replaced them with more CD style caps. These guys are electrolytic too, right? This one here, and there's 2 in here. This one is actually leaking and has spewed some fluid out of one end of it, so we know that it's definitely bad, as seen earlier. So that's kind of a quick rundown of some of the parts and pieces in this chassis. I haven't really gone and tested any resistors. The ones that are probably pretty close, I'll end up leaving, and I may change them all. I'm still kind of undecided yet. Usually when I get in and start testing, and depending on how badly wired this is, it might just be easier just to completely start over again. And go from there. So this guy was just tacked up here like so. You see that at the top there. So somebody's obviously opened it and tested it at some particular time. And, it's obviously in a pretty bad state of disrepair right now. So on to the next step. I'll start removing some components here, and I'll show you how to cleanly remove components, and when you're starting to do a recap or a re-resistor job, and how to go in and do that. Just before we go removing the components out of the chassis here and continue with the restoration, I'll give you a couple hints here. I've drawn up a small schematic here. If you're going to use capacitors that do have a banded end, say you have some polypropylene caps that have a band on one end, the band end always goes to the lower impedance portion. So the band of the capacitor will end up going towards the plate here, and then the other side of the cap goes towards the grid, and so on and so forth. So the signal path is really coming this way and going through like this and out. All right, and again, if you're going to be using capacitors with a banded end, the band you always want to go to the chassis or to the lower impedance point of the actual circuit. Now, a lot of capacitors nowadays, like these new polypro caps, don't have a band on them, and in order to get the optimum performance out of this capacitor, you kind of have to determine which end is the band if you figure that it's important in that circuit. And in the next shot, I'll show you how to determine which end is the band or the invisible band on these particular capacitors. This is how we determine the outside foil end of one of the newer polypropylene style capacitors. So this particular capacitor has no markings on it. It's just an epoxy dipped polypro cap. And we don't know which lead actually is shielding the capacitor, which lead attaches to the outside foil. And we can very easily verify that by using this old oscilloscope or any kind of oscilloscope and the coupling from our bodies. So we'll capacitively couple our bodies to this capacitor. How's that for confusing? And we'll use our bodies as a 60 cycle antenna in order to verify which end is the outside foil. So the scope I'm using is just a little OS8 style oscilloscope, and it's just got a directly coupled probe here. This probe is you know, this goes right into the center conductor, right into the scope. There's no capacitors in there, through a piece of shielded coax into the B and C connector here on the vertical section. All right. And what we're going to do is we're going to turn up the vertical section to extremely high sensitivity. Okay, so that's very high. You can see this is just picking up this noise out of the air, probably switching power supplies and the hum from my body. You see when I ground it out, it goes away. So you can see that it's just picking up random noise. So what we're going to do is take one of these capacitors. I'll grab this cap right here, okay? And we'll hook it up like this and look at the oscilloscope. So we can see that we do have some hum there, just from me holding this capacitor. So I'm capacitively coupling a little bit of hum into this cap this way. So we take note of this signal here, all right, and then we'll reverse the leads. And we take note of the hum there. Now we notice that we have a lot less hum introduced into the oscilloscope that way through my body. So that tells us that this end is the band end, or the outside foil end, because this end is now shielding me from becoming close to this lead right here, because this is the outside foil. It's connected to that one end. So we know now that this end is the outside foil end, and we could put a little dot on this end here of this capacitor, and we would know for the future that, and when we're going to put it in circuit, which side we want to tie to the chassis, or if we're going to put this into a guitar amplifier, we would know that this end of the capacitor would go towards the plate, and this would go towards the grid of the next stage. Okay, so now, if you have a whole bunch of these capacitors, you could test a whole bunch of them and see if they're all the same way. I don't know if they're going down the run the same way, or if some of them are backwards going down the run, and they're just printing the ratings on any old side here. But you know, if you tested 10 or 20 of these things and you determined that they're all the same way, you could be pretty confident that your whole batch is probably the same way. And then just put a dot on all of them. And if one was to go test a lot of capacitors, you could actually even make a small test fixture that would do this automatically. You just plunk this thing into the test fixture and have something that would introduce some noise into the outer side here, and you would know by popping all these into a test fixture which way the outside foil is. So we can see that this way here, when I hold the capacitor like this, it's less noise this way than when we reverse the leads and go like so. We can see there's a lot of noise. So we know that this is definitely the outside foil, because this is coupling to my fingers capacitively, and it's introducing that 60 cycle hum in the scope. So I have another capacitor here, and we'll hook it up the same way. So the lettering starts at this end here, okay, in the numbering. So I'll hook this one up the same way, and we'll see if this one is noisy too. Nope, see, this one is quiet this way. So this one is reversed. You see that? This one is reversed. So if I reverse these leads, you should see some noise. See that? So this one here, you couldn't do that. So these capacitors are going down the run any old way. This way here or this way here. They're coming down the run like this and getting stamped any old way. So these ones here, I couldn't verify by doing that. I would have to, put each one on the oscilloscope here and then just capacitively couple my fingers to it. So you could have your scope sitting on your bench and just do this as you're going, and it would be a very simple procedure for you. So that's how you determine the outside foil end. Whenever you're desoldering any wires from these porcelain tube sockets, let's zoom in here, that have fingers on them that are like this here, you can see how it's got kind of a tab here, and then another little tab here, and then the wire kind of runs up into the middle of them, and they've soldered them together. Don't bend these tabs if you can get away with it, because all of these tube sockets that have these tabs, if you bend them, they just snap right off. So what you want to do is just kind of very carefully heat it and then pull the lead out of the actual tube socket connection here. So put a bit of solder. If you need to add some solder to make a better thermal connection to get it out, sometimes I find that helps a lot. And then just pull the lead out with a pair of pliers, and don't bend these little guys, because they really do, they break off so easy. And then of course, when you're dealing with a connection that's like this guy here, what you really want to do is get your pliers in here, and they've got kind of little ears on them, you can kind of see here. right? And they've run this wire kind of around here and tucked it through. Now some of these you can get away with because they haven't really wrapped it or kind of coiled it around the connection. A lot of people do that, and a lot of companies did that, and that's one thing that I was really thankful for with the Tektronix Corporation, is they never did that because there really isn't a need to do that. It just makes repair very difficult. And what they would do is they just stick the component through and solder it, and that's exactly what I do. I never really curl them around unless it's a very high heat application to where that solder joint might, in the future become a little bit soft, and the component would fall out. But in a normal situation where there's just a small resistor that doesn't emit any heat and a capacitor attached to it, there really is no reason to wrap them around these posts. Now, I never remove capacitors midway up like this guy has done here. You see that? He soldered this onto here like this, and he's just kind of cut it, and that's how that fits in there. I don't do that. I'll remove the actual wire right at the socket itself. And it's usually pretty easy. Like, there's a lot in here that you don't really have to trim any ears off of. So I get my desoldering tool in here, okay, and put it here, kind of heat it up a bit. You can see that it just pretty much cleans that right out, and then you can just remove the wire. Now, I don't really need to remove this wire because it is a transformer wire, but I just used that for an example to show you. Now, a lot of people do wire wrap around these particular terminals, and then you have to clip the lead off or clip the little ear off, but this one looks like there isn't a whole lot of that going on in here. So this will be a little bit easier to get a lot of these components out because we won't have to worry about, trimming the tube socket. There's a bit of an art to that. If you trim too close to the tube socket pin, you cut an edge of it off. But once you get to realize where the ear is, if you just get your clippers in, I'll grab a pair of my sharp clippers here. If you get a pair of the clippers in at just the right spot, okay, so let's focus back down on that green resistor there. If I was to get in here and I wanted to get rid of this, I would come up to this like so, and I would pinch it right at this point, and it would cut that ear right off. These are very sharp, and it would cut it flush with that tab. And then when you desolder it, you've got a little bit of crud left on here. You have to desolder that, sometimes just by heating that up with your normal soldering iron and then flicking the tip off somewhere. Just flick the tip of the iron off. You'll clean these up pretty good. If you want to make holes, have the holes present again, a vacuum desoldering tool like this, HQ 470 with this 802 head on it is a very handy tool to have, right? So, of course, by having it that close, it's hard to read. So there you go. Like, this old HQ 802 works very, very well. Now, this HQ was modified. The HQ 470 itself is a very slow pump in it, and they do work very well. It has an induction motor in it, and I noticed that the HQ 470 is a much more reliable unit because it doesn't have a brushed motor. It's an induction motor. So I designed a drive for mine, and you can hear how fast mine goes. It goes, half to, a third of that speed, without the drive hooked up to it. So basically, I'm just changing the frequency that's going into that induction motor. But they have the HQ 470, and the 472 has a DC motor in it, and it goes very fast. The 470 has got great suction even at a low speed, but by speeding the 470 up, you really do get pretty incredible suction there, and it basically never plugs. But yeah, this is a great handy tool to have whenever you're working on old radio chassis or guitar amplifiers or anything like that. The tip heats up. It's part of the soldering surface. You could even solder with this if you wanted to. Have your solder in this hand and go in and solder with it because it works just as well that way also. So it's a great tool to have kicking around. And if you have one of those blue vacuum pumps, I think I've got one of them in here. Do I? No, I don't. I've moved them. I have the blue vacuum pump where you press the end in, and then it's got a little button. You press the button and it sucks the solder up. Those work very, very well too. And they're very effective in working in these particular kinds of circuits. You don't really have to worry about damaging anything with those. If you're working on printed circuit boards and you've got the big solder removing ones, sometimes the kickback can take the traces off the board if you're not careful. But in most cases, if you're careful, you can get away with using one of those pumps too. So what I'm going to do next now is I'm going to get rid of all these caps. I'm going to take all of these caps out and probably put in a lot of new resistors and get rid of everything in here and clean things up quite a bit. And I'm just going to move my way probably around the chassis. I'll come down here and then maybe move over to this side. And then this side here is going to take a while because people have really botched this up like you saw in the last couple of shots there. So I'm going to probably have to almost strip this entire section out and completely rewire it, start over again, and get that going. And then I'll have to find some sort of a can that will fit on the bottom here. It looks like a small tomato paste can would probably work. It's this is just a shielding can. It really doesn't do anything. It just keeps the injection level down so that you know, you don't get too much BFO injection by having this leak the signal out of here. So that's what I'm going to do next. I'll put some new electrolytics in here. Like you see down here, that one that was floating, put some new electrolytics in and fasten them up. And once I get to that point, I'll come back and I'll show you what I've done and explain that. Here I am starting the re-resistoring and recapping of this receiver. And you can see that there's a mixture of the Polypro caps here. And you can see there, I've marked all the ends. My oscilloscope's going on the floor there. And you can also see that I'm using disc type capacitors. And I've replaced most of the resistors in this area here. I'm still working on these. You can see these are all open and kind of hanging out here. And down into here I've replaced a lot of capacitors, and I'm kind of moving my way down and into this area here. So really, on this side I've just got to get rid of these, this guy here, these, and go down here and get rid of all this and clean it all out. I've kind of worked down to here. I've replaced the resistors down here, still got to get rid of a couple of waxies and so on. So there's a reason that I'm using two different kinds of capacitors here, and I explained that earlier a little bit. These particular caps are really good for RF bypassing, and I like using them in areas that I can to you know, to do efficient RF bypassing. Now there's a difference in these particular caps and these caps. Yeah, they both have the same rating and they're, you know, roughly rated around the same voltage, but these particular capacitors will move in value with heat. And you want to be careful about using discs around the actual converter area, and that's the reason that I'm using all Polypros. You can see they even have a mic on one of them. And by using these, you might actually add a little bit of instability, so you want to be very, very careful with that. So the Polypros are a little bit more temperature stable than these disc type capacitors here. I'm also replacing all the resistors that I can with metal film and carbon film resistors, just for added stability. You can see these are all here. This looks like there's a cap missing on here according to the schematic. I don't know if it's on the other side here. I'll have to check that. I'll probably go in there and replace that capacitor. Since this is a very sensitive area, I might replace that with an NPO style capacitor so that it's, you know, as the temperature changes, it maintains its value. We'll see how it goes as I go along. You see I still need to get rid of all of these tiny chiefs in here. All of this is going to go on this fella up in here. I've replaced some wiring in here. You can see the wiring that runs under here. This was, it looked like it was actually shorting at this point here. I don't know if you can see that dark mark there. It looks like it was shorting on there. So that might have been one of the reasons that this other fellow was in here so much. I don't know. It was kind of a hiding short. So I replaced that wire down into here. I have some old cloth wire. It's actually newer cloth wire, and it's got a plastic center in it, and it looks really good. So whenever I get a chance to use it, I use it in these old receivers. You can see the fellow before me has just used regular yellow wire. I might even get in there and get rid of that. So just going through and trying to choose the best components for the best area. There's a couple of areas that should be RF bypassed in this receiver that aren't, and they might have done that to cut costs. Because back in the day when they put these particular receivers together, these components, just regular components, capacitors and resistors, were pretty pricey. So nowadays this stuff is really cheap, and I've got a lot of this stuff. So what I'm going to do is you know, make the appropriate RF bypassing and such in this receiver to make it to improve it just a little bit. When I'm done, I'll include all this stuff on a schematic, and I might even post a schematic, or if anybody wants an improved schematic, or you know, if they're happy with the way that this receiver works, I might you know, have a schematic available. I'll see how it goes in the end here. So right now I'm just at this point here, I still, as I say, got to do all this, get down and get some waxies in here, and then I get over to the ugly side. I get over to this. Oh man, that's gonna be brutal. Can't see it here because I got too much stuff in the way. That's gonna be brutal. But I'll get in there and clean that all up too. And I noticed that there's another schematic on this particular receiver that uses two 6H6s, and they lose one gain stage in the audio. Now, I'm not too keen on that. I don't know if that was cost cutting or what they were trying to do there. But there are two schematic variants for this one. And I like the one in this receiver much better, so I'm going to maintain this schematic and still use that triode as the detector. And I don't want to eliminate one of the gain stages. They remove one triode in this to add another 6H6. If you look at the schematic of the variant of this particular receiver, you'll see that. So that's where I'm at this point. When I've got more to show, I'll be back. As you can see, I've got two Hammarlunds open on the bench now. This is a 129X, and this is the 120 I'm working on. No, I'm not going gung-ho and doing two at once. And there's a reason I have this other one open, and the transformers, or the filter chokes, I should say, laying around are a pretty good hint to that. So just before I get into that, I'll show you this side here. I've recapped and re-resisted these sides. You can see how I've mounted the disc-style capacitors in there, and all the new resistors. I haven't cleaned this up wire-wise or cleaned out all the little trimmings and stuff on the bottom here yet, so because I'm still working on it. So I've worked my way over to this side, and I've tested this filter choke here, and it's good. And this one here is supposedly the same filter choke. So this is the bad one, which is right here, which is number 20 on the schematic, is the bad one. And a lot of people complain about number 20 going open. And of course mine is open. So I've been doing a lot of reading on forums, and everybody says that, oh, the chokes in the 129 are the same as in the 120, and either you can just move them around and they'll work just fine. So I've taken some resistance readings. Now the DC resistance of this choke right here is 270 ohms, same size, same physical size. And the DC resistance of that choke is 270 ohms, same size. They look the same, and they're look like they would just be the same item. So being 270 ohms, same size, I guess a lot of people are getting confused, thinking, oh, the same choke. 15 henries, 129X, 30 henries, 120. Quite a difference in the two chokes. Double the henries in this one. So this is actually the offending choke that would be the replacement. This one is good. This comes out of the 129, and this is the one I was thinking of replacing, in this particular one here, using it. So this one reads 32 henries on the Genrad. So I'm imagining that the faulty choke over here would probably be the same, but I don't know, because now I'm seeing the differences in this particular filter choke and this one. So I've noticed something really interesting about this filter choke here, and I'll take my wide-angle lens off, and maybe you can see that. Move close to it. See the wire there? It's just wrapped around the actual lead-in wire from the transformer. The wire that comes off the windings is just wrapped around that wire, and there is no solder on it. So I'm thinking that might be the problem with these chokes. So I'm hoping, because I don't want to dig any further, so I'll open this side here, and I'll get into this choke and resolder both of these, and hopefully I can get continuity again, because the windings inside look pretty good. And maybe I can bring this one back to life and get some concrete ratings and see what their differences are in the 120 to the 129, because there's a lot of, as I say, misinformation floating around on the net about these. Some people say you can use 7 or 10 henries and that'll be okay. Well, it's quite a bit different than 30. So they're only using 10 microfarad, filter caps in this. So there is a lot of inductance in there. So, if you're going to take that down to 15, obviously you're going to probably want to think about the filter caps. Now they're only using 10s in this too. It says 10, 10, and 10. And they're using, these chokes. But this one here has got more inductance in there. I think they're using 10s. I'm not positive. They might even be a little lower in the 120. So I haven't really looked into that. I think I looked at the parts list, and they didn't actually mention what size the caps are. The original cap was here, but it's missing. Somebody was in here, as we know, and done a whole bunch of wonderful things to this 120. So one really neat perk about opening the 129 is I got the BFO cover out of it. So the BFO cover I can just put on here, and look at that. I can borrow that for now until I get into this 129. The 129's in pretty bad disrepair here. Put on my wide angle lens again. In pretty bad disrepair. The face is all carved up by somebody's fingernails. And I do have a replacement face for this, and all the replacement knobs, reproduction knobs. So one day it'll make a nice restoration project, but for now it's going to be a parts donor for this 120. Now there's they say the 120 was the improved version. We can see right off the bat one different part of the receiver here is the band switching. It's made out of porcelain here, whereas on this one it's just that standard wafer board material. So they were thinking of trying to maybe make the oscillator a little more stable. Not sure how effective that was. We'll see the stability in the end. And they also have like a plastic lead through in here. I don't know if you can see that in there. It's a plastic lead through. Whereas this one has just got a wire going through a hole, which I don't think would be too bad. So I might borrow some of the trimmer caps here, or I might just look around in my stuff and try and find some, but I might borrow some of these and replace what this guy, hacked up here and tried to stabilize this receiver with. Yeah, lots of reasons that this receiver probably was unstable, and I think a lot of it was due to these crappy Tiny Chief caps. So that's where I'm at this point. When I have some more answers on the filter chokes, I will maybe make a piece of paper and get this mystery all straightened around. So I've measured the inductance of this particular choke out of the Hammarlund. It's a 31 Henrys and 853 ohms. That's the DC resistance. And this one here, I've managed to find a winding. It's broken. This lead here, the red one, goes in here, comes back down, and goes almost right directly into the very center, or not the very center, but the very end of the core. And there's some small break in there, so I'm very close with this one wire here. And if you can see that wire, I've kind of pulled out of the core there. So I'll let focus on it. Get my finger here. See that very small wire there. So I've managed to pull that out, and from the green lead to there is almost 40 Henrys. It's reading 38.8 Henrys there. Come on, you can do it. Focus in. 38.8 Henrys in a Q of 11. But the DC resistance of this one is lower. It's down around 700 and something ohms. So this is almost, I would say, well, they're 39 Henry, so this is probably a 40 Henry choke. That would, make a lot of sense. So there's a very few windings left. There might, be one small winding left in there. So pretty positive. 40 Henrys, 30 Henrys. So this is what we're dealing with here. There's quite a difference here. I would imagine the windings in this are maybe were changed, and they've upped the thickness of the windings or something. They've done something, because these chokes don't seem to burn in the HQ-129s, but in these ones they do go. And yeah, as you can see, it's extremely fine wire. And at that amount of resistance, this thing is really going to end up probably getting a little bit warm. I imagine that this is probably broken somewhere, close to here, maybe on close to the core or something like that. It could have arced out or could have done anything, who knows. So what I'm going to do with this to make it good again is I'm going to connect a wire to this little broken wire, and I'll disconnect this from where it goes into the core, because obviously there was a problem at that point at one time. And what I'll do is I'll run this wire over to here, and that should make this choke okay to run again. And then that other broken part of the winding, because this is broken somewhere in there, will just be inactive. It's probably a few turns in there somewhere that just aren't going to be working. So it'll be very close to the way it was, and I'll be able to resurrect this choke. Of course, I'll feed it with some voltage and make sure that there's no arcing and there are no shorts or leakage to the actual core. So I'll check that all out and clean this all up. So there is quite a difference. So we're dealing with 15 Henrys here and 31 Henrys here. So it's 15 and 31 are the two chokes for the HQ-129X. And you can see the resistance of that is 273 ohms, and this is 853 ohms. And then this one here is roughly 40 henries, and this one here is 30 henries. And the DC resistances I haven't marked down yet, as I just haven't gotten to that particular point. But that's where I am. I'll probably edit in a piece of paper here showing the differences of the two chokes. So that'll go in right about here. And you'll see the differences in the henries and the DC resistance. Here's the winding that I've removed from the actual core. Takes a little bit of fiddling to get that core off. So this is an E and an I type core, and you got to be careful that when you do take this core apart, you're going to notice that there's a spacer under the I laminate, and you want to make sure that you don't wreck this, because this is for core gapping, and this has to do with saturation. So you can do a little bit of research on chokes and find out what that is if you're not familiar with core gap and all that. So what I'm going to do now is I'm going to reconnect this wire, and then I will fix this core up so that it looks good again, because I've done some carving. There's carving on both sides of this, and it's flaky like pie crust, this stuff, right? So you can see that little wire right there, it's coming out of the core, and so I'm going to have to reconnect a wire to that. It's very close to where it broke, so I'm not really concerned about the remaining couple of windings. They'll just be dead in there. They won't be doing anything. So this is where we're going to reconnect to, and that should give us around close to 40 henry. So we'll have our original filter choke back in the machine again, and it should be okay. I can also do a little bit of extra insulating to make sure that this doesn't arc out to the actual laminations here, and that is very important. So that's where I am at this point. Here's the repaired filter choke for the HQ-120. You can see I've put a new wire in here, and I've super glued it to the existing varnished paper inside here. It's very solid. And then of course it has this on top of it. And then under here there's a piece of Kynar soldered to that wire, and it runs up to that little piece of winding that you saw poking out before that was tinned. And it's soldered to that, and it's lacquered and insulated underneath. This here is the existing wire, and it's stuck into the actual lacquered cardboard really well. I didn't want to have to break that out to put a new wire in there. So all I did was I just put a piece of the sheathing, high heat silicone sheathing over top of this, and that'll be just fine. The wire is absolutely perfect. So there it is, the repaired filter choke for the HQ-120, ready to go back into service again. Now that I've got the filter choke taken care of, I can get back into the circuit here and try and straighten this mess around. So we noticed earlier this one here said 6H6, they've got marked here, and it's actually supposed to be a 6Z7. It's stamped on the socket, so that right there tells me that it's this schematic. Well, so we can see there's two schematic variants. See this 120X here, and it has two 6H6s, whereas on this schematic it's the same thing. It's an HQ-120X, but it's got a 6Z7 and a 6F8. So what they've done is they've removed this 6Z7 and replaced it with a 6H6, and still tried to use one gain stage in the 6F8 here. They've got a 100K resistor on the plate lead, which is pin 3 here, whereas in the schematic there's supposed to be a 10K resistor. Here they've just got a 50K tied to ground with a cap running up to this noise blanking switch. I don't know what the heck they've done there, but you can see this 50K here runs out to a bunch of other resistors and goes to the manual AVC switch. And so I don't know why they've tied it to the noise limiter switch. I don't know what they've done. We can see that this is clearly a 6H6 that they've intended to put in here. We can see pin 8 and pin 4 are tied, and then the lead runs up here to the limiter switch. So if we look here, pin 4 and 8 are tied, which are the cathodes, and they go right off to the limiter switch. So they've definitely tried to copy this little part here. So I don't know what they've done in here. As I say, this is all really hodgepodgey. This isn't correct to this schematic, and I could sit here and try and trace this mess and draw it out and try and figure out what they were thinking, but chances are it's probably some modification from maybe some magazine way back in the day. a lot of magazines came out with modifications to these radios and how to, maybe make the best of both worlds. And somebody got in here and tried to do that, or who knows what the story is. But I'm going to restore this to this schematic here, and I'd like to use all these tubes, the 6Z7 and the 6F8, and see what the performance of this receiver is like with those. If you use this schematic with the 686s, you lose one gain stage in the audio. You can see the 6V6 here, the grid line just runs right up to here, and there's no amplification. It just basically runs into the detector area. Whereas here you can see the grid line on the 6V6 goes into an audio gain control, and it clearly is coming off the plate of the 6F8, and then the grid runs up into the detection area. So, you're losing one gain stage by doing it like that. Mind you, I don't think the gain would be too high. There's only a 10K resistor on the plate, but I don't know what they were thinking, and I'm not even going to try and figure that out, but I would like to just see what they've accomplished and take measurements off this and play with this design here, not this one, because to me this one here seems like the chintzy design. So here I go. Time to clear this area out. Here's this section all cleaned out. You can see that the tube sockets have been almost all cleaned off. I've removed the cathode resistor and the capacitor and all the wires and all the junk off of this. That was all really confusing. Haven't removed anything out of the BFO can because this appears to be correct. It's just they've added 2 pink caps. So I'll go in there and I'll fix that all up in the end. And just one thing at a time here. These wires up here all seem to be in the correct spot. You can see those up in there. Those all seem to be in the correct spot. And I've tried to put the appropriate wires from the transformers in the the correct spots on these terminal tie strips here to get started. This is the audio output transformer lead. One goes to ground, the other one goes up to this jack up here, which I've completely removed in order to get into this area here. And see, what else can I tell you? I've removed the line cord, got rid of that right now, and disconnected it from here, and disconnected the AC. And got rid of all that. So basically I've just kind of cleaned this whole area out. I'll have to replace this wire that runs up to the top to the grid cap of the 6F8. It's crispy, it's a rubber wire in there, and it's all broken. And yeah, just start over again and copy the schematic over here and turn this back to its former self. So that's where I am right now. The bottom half of this Hammarlund has now been recapped, and most of the resistors have been changed, with the exception of just a couple. So this resistor here is still factory, or it's the original one that came with the radio when I got it. It's 3000 ohms, and it's the plate supply for the voltage regulator. And the fixed capacitors I've left behind are the fixed capacitors on the oscillator coils. You don't want to change those caps unless absolutely necessary. And I'm not talking about the compression style trimmers. In behind there's some red fixed mica capacitors. You don't want to have to change those, as I say, unless they absolutely fail or something's haywire, because many times they don't tell you this, but they're hand picked at the factory in order to make the actual dial accuracy correct on these old radios. So if you don't fiddle with those, you're probably better off. There's a lot of things that do affect the dial accuracy now, and a lot of it is just due to the change in the coil Q of the oscillator coils. The forms are drying up, and the varnish on the actual windings or the little wires there is changing. And that all changes the Q of the coil, and changing coil Q also changes the way that the band or the dial will actually align up. So the whole idea is to get it as close as you can, and usually they come pretty close still. They're for an analog dial, they're pretty good. So you can see this whole section is put all back together again. The 2 filter chokes are back in. It's got brand new Rubicon 500 volt 10 mic caps, 3 of them. I put a bit of silicone here to fasten them to this to the filter choke. This is actually a ways off the filter choke, and there's just a little puddle of silicone underneath there, just so that these don't shake and vibrate around if you ever move the radio, kind of thing. So this is the silicone. It's a GE silicone too, and it's the non-acetate kind of silicone. It doesn't have that horrible vinegary smell. It's a really mild smell, and you'll find that won't really harm the metals that it's applied to. So you can look into that if you're going to be using silicones on anything. You want to use the stuff that won't cause any kind of metal corrosion. So I found that for my own purposes, the GE Silicone 2 stuff works very well. This one has no silicone under it because it's pretty, it's pretty firm here. You really have to move it in order to make it move around. So there's 3 brand new filter caps. This whole section has been basically returned to stock again. So the noise limiting circuit and the whole audio section here has been converted. I've left one resistor out here for experimentation because I don't really like the value of what they've chosen. And I know why they've chosen that value. That's the 10K plate resistor on the 6F8. That 10K plate resistor is very low, and if you have a schematic there, you'll see on the schematic they have a 1000 pico or a 0.001 mic capacitor going to ground from that point. Well, what that does is that kind of cuts all the highs out. It really, really limits the highs off in the radio. And when I listen to radio broadcast, I like to have a little bit of fidelity there. I don't want it to be totally cut to communications quality. So I'll play with that value, and I may include the tips or notes in the end of this video. And if I do forget something, you can leave a question in the comments, and I'll answer it to the best of my ability, and try and help you out there. The BFO has been completely rebuilt. It's got brand new caps in here, and that's all redone. This tube here was originally a 6Z7G. I've modified the tube socket so that it will also take a 6N7, and that's the tube that I would prefer to use because it's a shielded tube. And it has a little bit higher current draw on the filament, but the transformer in this Hammarlund is ample to deal with that. The pinout is the same. Everything is the same about the tube. It's a Class B amplifier. The 6Z7 is a Class B. They're both dual triodes. The pinouts are the same. They're both high mu triodes. The only difference is the 6N7 can deal with a little bit more power than the 6Z7G, and or I should say that it has better dissipation ratings, better wattage ratings than the 6Z7, and it's shielded. So I would prefer to use that tube in the noise limiting circuit here. But at any point in time, I can just pull the tube out and swap it in with another tube. It's no big deal because they're wired the same. Pin 1 on the 6Z7 has no connection, and pin 1 on the 6N7 is the shield. So pin 1 is now grounded, so when I plug that tube in, the shield of the tube will be grounded. And everything else is in there. A new cathode capacitor on the 6V6, new resistors on the cathode of the 6V6. There's two 680 ohms, which make 340 ohms. They're in parallel here. So it's only 10 ohms shy of the original value. The 6F8, when you rebuild this, you probably won't ever have to go into such an extensive rebuild as I've had to do on this one. This one was really hacked up in this area here, but if you ever have to, strip a section out, it's crucial to pre-plan the use of your terminal tie strip here, because when you populate this tie strip, you have to keep in mind everything that's going to be around. And I left this one terminal open so I could tie the cap from the volume control to it, and then from there it goes to the plate supply. And that also gives me a tie point to tie in this plate resistor into the B+ lead. So there's things like that that you have to kind of pre-plan. The grid cap of the 6F8 comes through this rubber grommet over here and then comes out, and it also ties to this pin here. So you kind of want to make things close to where they have to go and where they lead off. So a little bit of pre-planning, and you're kind of off and running in that way. I've tested the resistance from the high voltage section to ground, so the resistance from the cathode of the 5V4 to ground and the output of this rectifier to ground. You always want to test the resistance before you fire one of these radios up, because if you have a low resistance, say a couple of K ohms or lower, you are risk opening this choke again. So the resistance to this in the high voltage section is very high right now, so I don't have to worry about that. It's there's no short circuits. You want to make sure that there are no short circuits before you fire this up, because this filter choke is a real sore spot in these HQ-120s, so I'm beginning to see. So now that I've basically found the problem and tapped that winding off, I don't want to ever have to do that again. So this is the reason I'm using some pretty good caps and everything. Everything should just be fine after this point, I'm pretty sure. So at this point, I still have to put the 6N7 in. I've got to go dig one out of my tube supply. And this is a 6K8 converter over here. I don't have one of those. This radio was missing those two tubes, if you recall, when I first got it. So I'm going to go dig some of those out. I'll put those two tubes in. and we'll turn the radio on and see if we can get any life. Now, I haven't tested any tubes in this radio. This is all just completely the way it came. What you know, or what I know right now, is what you know, and vice versa. There's you know, I haven't fired the thing up. It's going to, this will be its maiden voyage. So I'll hook an antenna to the antenna terminals down here. The speaker is still inside. I still left that speaker inside. So I'll have to end up replacing that. And in order for me to tune the IF coils and go on the top of the chassis, which I'll be doing next, I do end up having to remove the case. So I'll have to take out all the screws in the face, and there's 4 screws on each side of the radio here. And I can remove the case so I can get at the IF coils. The IF coils, they tune from the side, and of course this is solid here, so I can't tune them at all. So the whole thing has to come right out. And that'll be the next step. So I'll go dig out some tubes, and in the next little bit here, we'll fire this thing up and see if we can make this thing work without any smoke. Okay, well, we're just about ready to try this out. I've put the tubes in it. I found a 6K8 and a 6N7. And now what we're going to do, just before we turn this thing on, is we'll center the antenna compensator, okay? And how, when we first try this thing out, we want to have the crystal selectivity off. We'll have the phasing sitting at 12 o'clock. We want this to sit on receive, because if it's on send, we won't hear anything. The sensitivity will have maxed out. We'll put this on 54 to 1.32 megahertz, so it's basically most of the broadcast band in this position here. The audio gain is not off, but it's on 0. If we turn it off, the radio's off. So we want it on 0. We'll just have it down low. And actually, maybe we should have it up around 4 or 5. Let's turn it up around 4 or 5 so that when this thing comes on, we'll actually start to hear something if it does anything. I'll have the limiter off. I can have it on manual, automatic voltage control, or beat frequency oscillator. We'll have it on AVC. And what the AVC does is it automatically turns the gain of the sensitivity up and down automatically for you. So by having this on AVC, it's set to a level to where the receiver doesn't distort, but it's enough gain to make the receiver really work quite well. So it won't allow it to distort really. That's if the AVC is working correctly. So we'll leave it on AVC, so that just will kind of govern things. And the beat frequency oscillator doesn't really matter because we're not on BFO, but we'll just have it pointing at 12 o'clock. So that's where I am. So I'll focus this down here, get the light off the face, so that when I turn it on, you'll start to see the dial lights come on slowly. Now I'm going to hook the voltmeter up over here in the background. It's on DC, and I'm going to monitor the high voltage section and make sure the high voltage comes up properly, because if there's a problem in the high voltage section, we don't want to risk hurting that actual filter choke. Now we tested it, the resistance is high, everything should be okay, but who knows if something's going to arc out or something like that in here. You got to remember, in these receivers you're dealing with really high voltage. This will be in excess of 300 volts inside this receiver. So if you're ever working on one of these things, you want to be very, very careful. You don't go touching anything while the unit's on. If you ever repair one of these things, or if you're following along, you're definitely doing this at your own risk. So be very, very careful. If you're not sure of what you're doing, don't do it. Don't even work on one of these things, because they contain some really high voltages. And when there's no load on the power supply, they go very high. So now what I'm going to do is turn on my Variac over here. I'll move the camera. My big old Variac on this side. I've got the Variac down, and I'll turn it on. Okay, I want it, it's at 0, but I want it to current limit, so I'll put it on current limit. And I'll start advancing the Variac slowly, and we'll watch the dial lights on the receiver and the voltage. So you can see we're at 244 millivolts. That's basically just a static voltage there. So I'm going to turn this on. I'll start advancing the control. You can see the dial lights are starting to come on. That's a good sign. And we can see the voltage will start climbing once the cathode of the rectifier tube starts to warm up. And it's starting to warm up now. So it'll start to climb, and it's a good sign that it is climbing, because if it wasn't climbing, we'd probably have a short somewhere. And it's climbing quite easily, and that's really fluid too. So there's no problems there. It's just about up to 80 volts. Now you see it's going to climb down again. The reason it's climbing down right now is because the rest of the tubes in the radio are warming up and they're starting to pull current. So it'll settle off, and then it'll start to, it'll find kind of an equilibrium like what it's doing right now. So it'll first rise, and then of course the other tubes, as I say, they're starting to, their emission is starting to kick in, so it's starting to drag the supply down. So I'll advance it some more. And you can see it just climbs very slowly. And it is fully current limiting. Now this particular radio has quite a bit of current draw. There's lots of tubes in here, and it does draw lots of current. And you can see the lights on my control are lit, you know, not super bright, but they are bright. And they are lit up like that right now because it's current limiting. So now what I'm going to do, since I know that this is most likely going to be okay, I'm going to throw the current limit switch to straight through. So TH stands for through on the switch. But I'm going to turn the variac back down again. So I'm going to shut this down, and now I'm going to bring it up slowly with no current limiting and watch the action of this radio. So we'll take a look at the face of the radio, and you'll see the voltmeter in the background there again. So what's going to end up happening here is I'll turn this all down. All right. Now it's through. So now there's no current limiting. So I'm going to bring it up. And here we go. Oh, we have life already. Look at that. Oh, that's fading out. Oh, it might just be conditions. So let's roll the dial around. You can see the high voltage is pretty high. It's above 300 volts. So I'll just roll this around. So now if we fool with the antenna compensator, that'll tune the antenna. And tuning the antenna is very important whenever you're dealing with anything in radio, because having the antenna tuned correctly to the radio is matching the antenna to the receiver, and by matching the antenna allows you to receive better. So let's try tuning this and see what happens. So you tune it to the loudest spot. It's right about there.
On real time that they're in good standing. So
nice thing, the S meter is working too. I don't know if you can see that in the camera. The needle's moving a little bit there, which is a good sign.
To 5 centimeters over higher terrain with a low +1.
Not bad. Not bad for a first go. No smoke, and we're receiving radio signals. It doesn't get much better than that. So let's test some of the other functions. Let's make sure I got everything right here. So when I turn the BFO on, I should hear a whistle when I get onto a frequency. So let's find a frequency here. Hear that noise? So the BFO is working. That's good. Now the manual, it should get quite a bit louder when I take it off of AVC, because that's not, you know, controlling. There's no automatic voltage control anymore. So I'll turn it on to a frequency. Yeah, it's getting louder, and the needle goes down. I'll go find a stronger frequency.
Style cube in the world.
Yep.
Use 11:30 time, 5:13.
So that the AVC line is working. Let's try the crystal selectivity, see if there's if it narrows it up at all. Yeah, the crystal's working in the crystal selectivity. Boy, it's really narrow. Keep grabbing this knob, it's the wrong one. This one here doesn't really affect anything right now. This is the one I need to be focusing on. Not bad. So it all seems to be functioning right now. So this is a very good start. Now keep in mind, no tubes have been tested. It has one new 6N7, and that's only the noise limiter. We should try the noise limiter out. I'll see, turn the audio gain down, turn the crystal selectivity back off. See if I can find any noise. Man, it's pretty quiet. I'm going to try another band. When you rotate the band switch, if you hear static when you rotate the band switch, you can pretty much be assured that the oscillator is working. So I'll turn this up. Yeah, it's clipping the noise. You can hear the difference. So the noise limiter is working. What I'm going to end up doing one day, and I'll probably have another video on this, is I'll make a random noise generator to test the noise limiters in these old radios. So basically it'll be like an old commutator type DC motor with an antenna on it, something that'll make a horrible noise, and see if this can trim it out. And that would be another neat video to make sometime in the future. So I'll probably do that, and then it'll help me test out the noise limiting situation. It's quite quiet here. All of our power lines are underground around here. And I'm right at the top of a hill, so I can walk up to the end of my street and see for miles. It's I'm up quite high, so this it's really relatively low noise up here. So you can see the noise limiter is working. So let's go back to the band switch again. If you rotate the band switch and you hear static in each particular part of the band switch, you can pretty much be assured that the oscillator is working. If it goes quiet, like I'll go between here. If it goes like that, it's pretty much, you can tell that the oscillator's dropping out. So I'll turn it up and I'll rotate it. Yep, it's working. That's a little quieter, but it's because the antenna compensator isn't picking up any. There hasn't compensated the antenna here, hasn't tuned the antenna, so that's working. No problems there. Yeah, see, oscillator's working in every position. So I'm off to a really good start here. Everything seems to be working pretty much right off the get-go. So now the next thing to do, what we're going to do is open the case up, go inside and start looking at the IF section and start tuning the IF. And we'll look at it up here on the spectrum analyzer again. We'll look at it on this spectrum analyzer here and see how wide the factory IF transformers really are inside of this particular receiver with the, of course, no crystal selectivity on. I want to see how wide they are, left well alone. And of course, and then we can check the crystal selectivity positions here and make sure. We also have to locate the actual crystal frequency itself. So usually they're not right at 455. The IF for this is 455. So I would like to, I'm hoping that the crystal is very close to 455, and if not, we might be able to modify the crystal to bring it to 455, because if you drag this too far from its original IF, that will affect the dial accuracy too, and you don't want to do that. So we want to keep it as close to 455 as we can. But that will be the next step. Here's a quick video to aid you in realigning the dials on your Hammarlund HQ-120, 120X, 129X, 140X, any of these particular radios. And it's pretty simple. So if you're going to remove the dials, don't worry about indexing them because there's no need to. First, you'll have to have this cover off here of the actual variable capacitors. This cover has to get removed, and of course you got to remove the face. That's pretty self-explanatory. Remove the knobs, and of course take the nuts off the shafts that need to be removed, right down here to the headphone jack, and then the whole face should come right off. Okay, at that point you've got a couple of set screws on the main dials. Undo these set screws, just enough so that the shaft is loose. You have to undo it. The shaft itself has a groove in it, so you don't want these screws to get caught in it, so undo them maybe a turn or two. And the same with this one. And then what you've done is you've loosened the shaft off, and then they're usually pre-oiled or lubricated in the center, and you can just very simply slide them back. They put grease in them from the factory, it seems. And then all you do is you pull this forward, and of course with the gear being out of there, and it's not yet, so I'll push that back a little further, and you pop this out. Now the edge of the dial itself here is driven off of two washers that are spring-loaded on this main shaft under here, and you'll have to get the edge of the dial back between those two washers. That's not too hard with the use of a flashlight, and you can see the two washers down in there. You have to get it in between those two washers down there. Not too hard in the end. When you push this gear back, light back here, when you push this gear back, you can see it's going to it's going to come out of the main gear. Now you're going to lose spring tension on that gear. Now those two springs hold tension on this smaller gear, and it reduces the dead time when you're tuning it, so there's no slop in the gear. So you're going to have to basically take these two gears and move them apart, one way and one the other, until the spring has a bit of tension on it. It's usually about halfway through the opening here. And then you can lock it with a just a screwdriver or something. Put a screwdriver in the actual gear, like so, and that'll lock it when you're actually going to push this gear back in and put the dial back together. So when you're putting the dial back together now, you've got it out. It's pretty much that simple, and it goes for both sides. So what you're going to do is you're going to put this back in here, and you have to get this right between those two washers down in the bottom. Okay, so that takes a little bit. You'll have to use a flashlight. You can look down in here like this. I won't bother right now because it's not too important in this video. So of course you've got spring tension on this gear right now, and I can't do that with one hand on the camera and one hand on the gear here. So say there is spring tension on this right now and it's been locked. What you do is you just push this gear here back in to the pulley, or back into the actual dial, I mean. Put it in like that, and then get the gear in. Doesn't matter what position it's in at this particular point, okay, as long as there's spring tension on this gear. So now you can see your dials back in. Now what you do is you rotate this dial. You see this stop here on the back side of the dial? You rotate that until it hits that. See, it hits that there. Rotate that till it's tight. Mesh the capacitor. So this capacitor here is fully meshed. Okay, so that means that it's at its you know, the lowest end of the band at this point. So just mesh it so it's completely flush. All the plates are flush. You don't want it kind of half sticking out, or you won't align it properly. So make sure they're flush. Make sure this is at the stop, and then tighten these two screws up, and your band is realigned. That's that simple. So now this doesn't, of course, have anything to do with the RF alignment or anything. This isn't going to get you if the actual band scale is off according to the stations. You have to go underneath and adjust the padding and the trimmer capacitors, I should say, and the coils. You have to adjust the compression style capacitors underneath the chassis. Adjust the top ends of the bands, and the coils adjust the lower ends of the bands. But that's the same, and it's the same thing for this one. You'll notice that this one is at its stop on the other side. So if I rotate this around here, this is at its stop, and you'll notice that this sits at 12 o'clock, this one line here. That's its alignment point to that black line on the window. And it's the same with this one. This is the alignment point here on that one. So don't get it confused with this line here. It's this one here. And of course, when it's at the stop, this should be, you know, pointing at 12 o'clock. And when this one's at its stop, this one should be pointing at 12 o'clock, and that's where you tighten these screws. Remember to fully mesh both capacitors. They have to be fully meshed, all right, so that they're flush. All the plates are flush with each other on this one and this one, and then you can tighten down your screws, and it's pretty much the dials will be ready for calibration after that point. If you remove these dials, be prepared to go underneath and readjust all the oscillator coils and capacitors underneath, because your dial is going to be out if you remove these, most likely after this point. So this is handy to do if you need to clean the chassis off or take the dials off and clean them or anything. It's not a big deal. Don't worry, as I say, about indexing the shafts, because chances are if you're restoring this radio, it's not in alignment anyways. And this would be before you do any RF alignment. If you do an RF alignment, then take the face off, you're kind of going at it backwards. So make sure you do the chassis cleaning and remove the face first and everything. And then right in the end, when it's pretty much solid and ready to go back together, is when the RF alignment and the oscillator alignment and everything will just take place. Hope this helps. Alright, so I've cleaned the radio up inside and out pretty much. I've cleaned off the chassis and cleaned the face up, as you can see. I completely removed the face, went inside the S-meter, tightened that glass up, so it's now tight in there. I re-blackened the spots on the meter because they were kind of fading and the light was shining through them. Didn't look very well. And cleaned the dials up and took everything off and cleaned it. Now I'm just working on the knobs, cleaning the knobs up. I'll put the knobs back on, and we can get into the alignment here. So I've got a little trick to show you with fixing the knobs up and making the knobs look a little bit better, and I'll show you that here in the next shot. So if you've removed the chicken head knobs off your radio or anything that you've got really with baked like chicken head knobs. You'll notice that a lot of the times on these old radios they're yellowed or discolored, or the paint's missing out of that crack there, and they're just they're not looking like they should anymore. So eventually you'd like to end up with a product that looks like that, nice and clean. You see that, how nice and bright white that is. So that's a very simple process, and I'll show you how to do that. All it requires is some whiteout. That's it. So all you got to do, I use this Bic stuff. It works very, very well for me. It's very simple. I just open the bottle up, give it a good shake first. Open the bottle up, and all you do is you take it and you just smear it right on there like that. Okay? And then what you do is just let it sit. It's very simple. Let it sit until it dries and gets hard. And you can kind of, if you want, get rid of some of the excess on the edges. It's not a big deal. It's already drying though, so. And just let it sit like that for a few minutes, and when I come back I'll show you how to make it look good. Okay, so the stuff's dry now. So all you do is take your fingernail, like so, and just scratch the excess residue off. You can even scratch right over top of the line. It won't even affect the line in the center of the knob. So I'll just do this quickly. It takes a bit of time to get all of the whiteout off of the chicken head knob, because it does find little cracks and crevices, and you kind of have to clean it up a little bit. So a Q-tip is your best friend too. You can use that and scrape with a Q-tip. You can see how that helps out. You want a soft substance. Don't scrape it with a screwdriver or anything like that, because then you're going to scratch your chicken head knob up. Okay, and you can also use a Q-tip. I've got a Q-tip here, and I use a bit of rubbing alcohol. So I'll just put a bit of rubbing alcohol on it. You don't want it dripping off the end, but you just want the end kind of wet. And you can go in here, and that'll aid in your removal of some of the bulk of it. Of course, you don't need to be as sloppy. You can try and just paste it right on the line. The nicer that you are with the whiteout, the better the final product is going to be. This is just a very fast demonstration to show you how well it works. So you can see it's already coming together and looks very, very nice. It's much nicer than it was before. In order to get all the lines nice and trim, you got to work away at it a little bit. And once you work away at it and get all the little white spots off, like this, and then of course there's a little bit in there. And a little bit on the end there. Anyways, you get the idea. Just keep working away at it, and eventually you end up with a pretty nice looking chicken head knob with a nice clean white line on it, and much better than it was before, all that yellowing and grossness. And it really adds, especially when you've got a nice clean face on your radio, having that nice white line there really does add to it. So there you go. Hope this little tip helped. We're now at the point to where we need to tune the IF in this Hammarlund HQ-120. This also applies for the 120X, the 129X, and also the HQ-140. They're all very similar, and the IF sections are all pretty much tuned the same way. So in order to do this alignment procedure properly, you do need a visual means. You will need either a sweep generator or a spectrum analyzer. A signal generator alone and an oscilloscope or a voltmeter on the AVC line just will not work for this particular receiver, and I will show you why. And it will also not work for the 129 or the 140X. So now what you see on the screen here, I've pre-tuned the IF here because this is about an hour and a half twiddling the IF coils in order to get this response pattern. And the reason it takes an hour and a half is because you have to figure out where the maximum sensitivity is and how high up on the scale that is, and then you want to listen to that on with some radio stations and go, wow, that's really kind of ugly sounding. So then you widen the pattern out a little bit, and you widen it out a little bit more. And as you're widening the audio response pattern here, the center is going down. The center is your sensitivity here, and this is your audio response. So as you're widening it, this goes down and down and down. So you want to find that happy medium to where you have, the best audio response for a given amount of sensitivity, and this seems to be the equilibrium point. And that equilibrium point is, if you look at the marker on the screen, right about here is 4 kilohertz, and the 3 dB down point is about 6 kilohertz wide. So that's about the best that you're going to get. If you start to narrow it any more than that, your audio will really start to suffer, just due to the audio section in this radio and the way that the transformers are designed. This is designed for communications quality audio. And when you try and stretch out these transformers too wide, you really do lose the sensitivity. So now when I say that you really can't tune this receiver with just a signal gen and an oscilloscope or a voltmeter, I've tried it. Tried doing it with that method just for the heck of it, just to see if we could do it and get around, the manual and doing it like this. But there is one thing that is a real catch-22 with this particular receiver, and that catch-22 is the crystal selectivity section. Now, when you tune this one transformer here on the top, this guy here, this guy not only tunes a peak, but it also drags this crystal around. So what happens is that you find the crystal frequency you're at, and you go and peak everything up, and you find that it's shifted the crystal frequency again. So you're like, I got to go through and retune the IF section again. This is, of course, doing it with the signal generator method, okay? This isn't the sweep gen, this is the signal gen method. And using the AVC line or an oscilloscope. So now you go through here, and you re-peak everything up again at the crystal frequency, and you peak everything up to find that the crystal has shifted again. And you're wondering, why does this keep shifting? Because at this point you don't have a visual means, and I hadn't hooked up my spectrum analyzer at this point, or any kind of sweep generator at this point, and it just keeps shifting, and it gets really frustrating. So you keep moving this slug around, because this is the one that keeps doing it. Well, I can tell you that, you see how this shaft is broken here? This is from the previous guy that's tried to align it, and I can guarantee you that he did this with the signal gen method, and he was moving this so much trying to find it because it keeps shifting, he actually busted the little shaft here where you stick the screwdriver in. So I had to tune this with a pair of pliers. So that is pure proof of the result of just a signal generator tune-up job on this. Another interesting thing was the set screw, or the actual, the tuning screw in this trimmer capacitor on the side of the phasing control was also missing. So I was thinking, maybe they, at the factory, it was just, used as some form of a gimmick, and, it was at its maximum capacity. But then again, you look at this and you're like, yeah, well, somebody's probably done that, taken it out. So, and of course, without tuning this visually, there is no way to know where that little screw is supposed to be turned to on that trimmer cap. A lot of these units don't have this trimmer cap, and they have a black wire in the lid here. That black wire does the same thing that this trimmer cap does, and what you need to do with the black wire is not bend it out close to this tab. Don't do that. Leave it close to the center of the lid here, and you move it back and forth with the visual means using your spectrum analyzer or sweep gen, and you tune for electrical 0 of the phasing control. Now, that's not the 0 on the face. That's the phasing control pointing at 12 o'clock. That is the electrical 0. All right. So I will demonstrate this quite shortly and show you what I mean. So don't move that black wire close to this, to this part of the lid here, because if you do, when you put the side cover on, it will couple to it and it'll change your response pattern. So you don't want to do that. So the IF coils that you need to tune, if this thing has been, say your radio has been extremely badly screwdrivered before you got it, and you need to tune the IF section just to get a peak in the beginning, that's fine. You can use a signal generator for that. all you want to do is peak these all up roughly to 455 in the beginning. So this is one you tune here, you tune this guy, there's two down in here that you tune this guy here, and then you tune on the other side the diode output link, which is right beside the BFO, and you'll have to tune all of those. You can leave the BFO alone until the end, but you have to tune all of these and bring it to a peak, and that alone will be a little bit time consuming. So this is the response pattern that I got with the crystal selectivity off. As I say, it's about 6 kcs wide at the 3 dB down point, and at the peaks here of the signal on the audio sidebands here, you'll see that it's about 4 kilohertz is the peak there. So that really sounds pretty good for communications quality, and it's a nice even cut between losing the gain. I'll try and edit in a picture here of a really sharp response pattern that I've tuned for. And that sharp response pattern will give you more receiver gain, but the audio quality suffers. So it really is all about that balance. So I'll tune the crystal selectivity control here to notch number 1. And that's how it looks. So right there you can see, like, you know, we're at just about the 3 dB down point. I'll go to the display line here. You can see the top here, and then we go down to about the 3 dB down point, you know, somewhere in here, without doing the math on the screen right now. You know, so really you're going to be looking at, you know, say we're you know, calling this, you know, 11 dB, so we're wanting to go 3 dB down. So we're going to go 14, right? That would be the 3 dB down point right there. So if you look, when I change the crystal selectivity, so really the response on this right now, if you look at the marker on the screen here, you see the response is from here to here. That's the response pattern that we're really hearing. All the rest of this doesn't really mean anything, right? Of course, it needs to be there for the signal to exist, but this is really where the audio is dwelling. Some people will go 6 dB down, but if you go 6 dB down, you like candies and flowers. That's all I can say. 3 dB down is about the reality point for the way that the audio is going to sound. 6 dB down, you're just you're living on hope. So there you go. So this is the response pattern from here to here. Okay. So now when I go to crystal selectivity number 2, you can see how much sharper that is. Now it's from here to here. All right. When I go to 3, wow, look at how sharp we're getting. You know, from here to here now. And then of course on 4 and 5 we get really, really sharp tuning, and we'll lose a little bit of gain here. You can see it'll drop down. And that's about what it does on the 4 and 5. That's normal on positions 4 and 5 if you have this tuned properly. So there you go. So now what I'll do is I'll explain how the actual crystal selectivity works on one of these radios. So the center frequency of mine is 455-300. So that's the center of my IF. And that took a long time because, of course, the cans pulling the crystal and you know, finding this medium here. So now the phasing control, setting it at electrical 0, is that trimmer cap on the side that we were just talking about, or that black wire. So mine was missing the screw, and when I got it, when I looked at my phasing control, like on the screen here, that was sitting at 12 o'clock, or electrical 0, and that was supposed to be 0. Well, that's not zeroed. So when you put that screw in there and you start tightening up that trimmer cap, you start to get the 0 like this, and you'll pass it and you'll go over to this side. So you want to get that electrical 0, which is right about there or so, okay? So that is electrical 0. Without that screw and without a visual means, there is no way to find that, because you wouldn't be able to tell if you're here or here. You wouldn't be able to tell. You'll hear a little bit difference in tone, but how would you actually know how to, you know, visually know that that is, you know, off to one side or the other? You just don't. So one, you know, very, very important reason to have this visual method. Now, you'll see when I tune the phasing control here, you'll see how it'll pull a notch onto one side. See that notch? It's moving up. And I can move that notch closer to the center, or I can drive that notch away from the center, or I can, if I go onto the other side of the center arrow, which is 12 o'clock, I can pull a notch up on this side. So say I'm listening to the frequency right now, wherever I am, I'm listening right at the center. So say I've got an interfering CW signal beside me, I can move this notch up. If the CW signal is right beside me, I can move this and put him into the notch okay, and kind of notch him down. As you see, I can move that notch further and closer from the center here. You see, I can kind of bury kind of a signal into the notch there. You see that? And I can do it on the other side. If he's above me or below me, I can do it on this side too. I can kind of just, you know, create a really, really tight notch there. And that's exactly what this is designed to do. You kind of just want to get rid of the adjacent frequency that's really close to you. Now CW, which is you know, Morse code, is just a pulsing carrier. So if you have him tuned right at the center, he'll get really loud because he's right at the peak of your IF. He's like right there. He's like right in the center. So the nice thing about that is really on the super tight selectivity thing here, you can see how tight that is. You know, I can move the notch here. You see how I move that around? When you tune him in with the main tuning control, the whole idea of tuning him in, I'll use the marker as a reference here. So I'm tuning around the band, and all of a sudden, look at how fast he comes up, and boom, the CW is right there. Now he's going to be really loud, and as I roll past him, he's going to get super quiet again because he's just going to fall right off. You see that? So that's how the phasing works and the crystal selectivity works, is whenever you tune a CW signal in, or even sideband on, you know, on the wider kind of controls, that's 2 and that's 1 there, you can really, as you're tuning them in, you can really narrow right into them and get rid of adjacent frequencies by using this as kind of a notch. And that works very, very well. So that's how the phasing control really works on these radios, and why you need to actually tune this with a visual method. So I very rarely use the crystal selectivity unless it's, you know, a really hard copy in the morning or something like that, or even in the evening or whenever. I'll rarely use it. I used to be on CW quite a bit, and that was really quite handy in those days. But now I'm just, you know, basically an AM guy, and I do some sideband too, listen to sideband, and you know, I will use the crystal selectivity maybe on this position or this position in order to get rid of some adjacent frequencies. But it really is quite a handy filter, and when they're tuned right like this, they really, really work quite well. And in the end, when I'm cruising the band, I'll demonstrate all of this and show you how this all works. So that is really how to tune the IF section of this radio in kind of a nutshell. I would go through it and you know, have the camera on this, but you would be watching me for about probably a half an hour or so tune this from nothing, and trying to get a single, you know, really good response pattern. And at the same time, I have to locate the crystal frequency and then drag everything over to its frequency. And you have to figure out how to do this without you know, moving that one transformer and dragging it off, and that takes quite a bit of time. And unless you actually do this with a sweep generator and fool with it for a while, there really is no way to explain this. It's just so much that you have to know, moving from coil to coil and moving back and forth. And what I mean is by getting your selectivity response by moving from this slug down here to this slug here to this slug and then back to this one, or from this one here, which will pull everything over and peak things up, and then going back to this slug or to this slug or to this slug or to this slug, and then over to the other side to the diode link. It really is an in-depth procedure. So a visual method is the definite thing to have. So next we'll be on to the RF tuning and aligning the radio. So I'm getting to the point to where I'm going to start RF tuning this radio here. And I figure, okay, and I'll go through the section here and check everything, and, you know, look at these particular caps here to see how good they are, and this, that, and the other. And I, you know, it never ceases to amaze me how some people modify radios, and this is a pretty good one. So what happens is the part you stick your screwdriver in here, like in a normal paddle here, is always connected to the chassis. So there's no, you know, connection between you and the actual coils, because, you know, if it was the reversed way, the minute you brought any kind of screwdriver with even a little metal insert in it, you know, towards the high frequency coils, it would drag it, you know, cause it to drift. You wouldn't be able to align the dial up, right? So I'm checking this out. I wonder what side this guy has attached these to. You know, has he attach it to the chassis side? You know, the side that's supposed to go to the chassis, which is this side, right? Because you stick your screwdriver in here. So this is supposed to be the grounded side, and you know, or what's he actually done? So you know, I figured I'd remove one of the wires and just check this out. And so this is the part that connects to the actual wire on the coil. Hear that? That's continuity. So this guy has installed all of these capacitors, these variable trimmers for the coils. He's installed them all the wrong way. So there's no way you can use a plastic tool on this or even a ceramic tool because these are so sharp. I don't know if you can see inside this thing. I'll get my light up here. Maybe I can shine a bit of light on it so that it'll focus on it. I don't know if you can see that, but they're like razor sharp in there. You can't actually, you know, put any kind of tool in there except a metal tool. And that's just the way these are supposed to work. You're supposed to actually use a, you know, a small sharp metal tipped screwdriver, and this side is always supposed to be the grounded side, so it doesn't matter, right? You know, it's not going to make any big difference. Well, trying to do any kind of alignment on this, if you bring any screwdriver near this, the minute you touch it, it's going to drag the dial right off because you're adding inductance from the actual length of the screwdriver to this. And you know, you're basically adding a big air pad or air capacitor off the coil up into midair, and you know, you could even be capacitively coupling it to your hand if you're using a small metal screwdriver or something like that. So now it's okay to tune these with an insulated metal tipped screwdriver. These ones here you can tune no problems because this side is ground. Okay, so this is grounded right to the chassis, and there will be very, if any, little coupling between the screwdriver and what you're actually tuning. So this thing here, these are all backwards. These are in here, so the minute you touch these, it's going to drag the coil big time. And, you know, it's just, I don't know what people are thinking when they're making these modifications. Like, I mean, that's just, you know, absolute silliness. So, as you can see here on my little meter, I don't know if you can see that there. I don't have to push any buttons with this meter. It just knows what I'm thinking. It's kind of neat. See that there? I got a glare on it from something, from this lamp here. Okay. You can see, you know, right on the back, the side that's soldered to the coil. See that? Just a dead short, right? So the side that's supposed to be is, you know, this side to ground, and you can actually see it's actually physically connected to ground. So all these are all backwards. So I'm just going to take the ones out of the HQ-129X, and I'm going to put those ones in here, and I'll just mark down the values and replace them when I work on that, because of course this is the receiver I'm focusing on right now. And what the hey, I still, you know, have to put this you know, filter choke back in it too. So I've got my work cut out with me just reassembling that thing. So here it is. I got to change all these out before I start doing my tuning. So note to self and note to everybody else, always check these. If somebody has ever installed some replacement trimmer caps in here, make sure they're the right way. And you'll have to disconnect this wire to read it, because the coil will just give you an actual continuity to ground itself, because it's going through the coil, right? See that? So you have to disconnect the lead to the top to actually check that. So with these ones you can actually see they're just, you know, soldered to ground. You can physically see the connection here along all of these. So what are people thinking? You know, like, you know, this is such a silly modification. You know, at least put them the right way if you're going to change the caps. No wonder this guy had problems getting this thing to tune. Maybe that was half of the problem. Who knows? Man, people. Hi there. We're now going to align this Hammarlund HQ-120 radio. And first thing you're going to do before you start the alignment is you're going to build this little adapter for the back of your radio to make your radio think that you're feeding a 400 ohm antenna to it. Most signal generators nowadays have 50 or 75 ohm output, and you want this in line with the hot lead into the antenna jack in the back. So one of your antenna jacks will tie to the chassis, and that'll be ground, so the negative of your signal generator will attach to that, or the shielded braid will attach to that. And then the hot side of that lead will go to here, and then this will go to the antenna jack. So you need to build this first. If you skip this part, your sensitivity of your receiver will be down if you tune it to an impedance of 50 ohms on the input. It's supposed to see 400 ohms. Second thing we're going to do is go to the dial of your radio, and where it says 200, you're going to adjust the band spread to where it says 200. So you want that at 200 right on the nose before you do any alignment. If you don't do that, your alignment will be completely off. You can zero your S meter or put it to the arrows. You can see there's an arrow here. There's a procedure for that. There's two VRs on the back of the radio. One will adjust the top and one will adjust the bottom. So at the top you can see it's on the arrow, and at the bottom you can see it's almost on the arrow. It's moved a little bit. That's absolutely fine, as long as it's relative and it's, centered enough. So with the RF gain or the sensitivity at 0, it should sit like this with no antenna. And with the sensitivity to its maximum, it should sit like this, right at the two arrows. Okay, that aligns that meter. Just roughly get it. Doesn't need to be right on the arrows for the alignment. As long as it'll, show you relative sensitivity, you're on your way. So the crystal selectivity is off. Phasing is at 12 o'clock. Send receive is at receive. Your sensitivity is maxed. This is wherever the dial needs to be. This is on the band you're going to align. We're going to align the 1.32 to 3.2 megahertz band. Audio gain is, somewhere relative where you can hear some noise. Limiter is off, AVC is on, and beat frequency oscillators at 0, and you can have this at 12 o'clock to start the antenna compensator. Okay, so now we need the data sheet in order to show us where all of these adjustments are and what coils do what and what trimmers do what. And that's on this sheet here. You can see it says rear of the radio. That is the rear of the radio, and that means that this is going to sit up like this, and that's going to be like this, so they match each other from the page to this. Now, before you go sticking any tuning tools in here, you need to have an insulated tuning tool, and you're doing this at your own risk. There's a lot of high voltage in here, and if you slip, you might buzz yourself really good. So you need to be very careful. If you're going to adjust this radio or work on it at all, you're doing this at your own risk. Insulated tuning tool for definite sure. It can be a metal shafted tool. Plastic ones you'll find won't turn these, will break the shaft off, so it does need to have either a metal tip and be insulated or some form of a screwdriver. Just do not touch this, because as I say, if you slip and come across that, there's 300 volts there, and that's 300 volts DC. You got to be very, very careful. Okay, so now what we're going to do is adjust the bottom band. We have it on the 1.3 to 3.2, and that's right here on this piece of paper. So we see that we have 3 coils to adjust this band. This first section is the oscillator section. This is what aligns our dial accuracy, and that's the front end here. Okay. The second one is the RF alignment, which just peaks up sensitivity, and so does the antenna. So that's what these all do. So we can see the RF. This is the oscillator, RF, and the antenna. So what we're going to do is align the bottom end of the band first, because it's usually the one that's out, and there's many turns of these coils you have to make to align them at first. So what we're going to do is go to the 1.4 megacycles here on the dial. It says 1.3 to 1.32 to 3.2. That just tells us the band. This is our alignment point. So it says 1.4 megahertz here, so we have to tune our main dial here. Don't touch the bottom band spread. Leave it at 200. Don't touch that at all throughout the entire alignment. Move this to 1.4, okay? So we're at 1.4 megahertz right there, okay? Now we need to go up to our signal generator here and tune. See where it says 1.4? We already have it entered, and it's at 30% mod, so we can hear a tone. And I have 30 microvolts coming out of this cable going into that little adapter on the back there, okay? So now we can't hear the signal, so what we're going to do is tune this coil right here until we hear a signal and drag this actual band around. Even though we're not moving this dial, we're moving it with this coil, okay? So I'll turn this now. So now I've just aligned the bottom end of that band. Now you'll have to go back and forth and do this a bunch of times, because what happens is it'll stretch the band out one way and move it in or make it shorter, and I'll show you that here in just a short bit. So now we'll go back to the second one back here, because we've adjusted the oscillator to bring it onto alignment. So now we go to the second one back, which is this one right here, okay? And what we're going to do is tune for a peak, look for a maximum signal. If you pass it, you got to go back. There it is. That's our maximum signal. Okay, so now we'll go to this last one and tune the antenna. This is really affected by that little RMA thing if you don't have it. And there you go. And then you can check to peak it to see how sensitive it is by tuning the antenna compensator. And there you go. So that's where our sensitivity sits on this band. Okay, so now that's the bottom end of the band, but now we have to go and adjust the upper end of the band. And that's at 3 megahertz. So we tune the dial here to 3 megahertz. Okay, so we want to get that right on 3, which is right there. Okay, so now we need to tune our signal generator here to 3 megahertz. Pardon the glare of the lights here. So 3, oops, I'm on modulation. I'll go here to frequency. Frequency 3 megahertz. Okay. So now we're at 3 megs, but we don't hear a tone here again because it's not on frequency up here either. So now we have to adjust this capacitor in order to bring it on. It's very easy to pass. See how touchy that is? So there we go. Okay. So now we have to align the RF stage, which is this one here, to bring up more sensitivity. That's right about there, and then we can try this. And we're about the same on both bands there. Okay. So now the antenna doesn't have an adjustment for that. It's only the bottom end of the band. Okay. So now we need to go back to 1.4 megahertz again on this band and check it to see if it's moved, because a lot of the times it will move now. So we'll go back to 1.4 megs here. We're at 1.4 megs on the dial, and we'll type 1.4 megs in here, 1.4 megahertz. And we're really close, but it's still off. So we're going to go and readjust this coil again. See that? You can hear it how it was tuning in. And we'll adjust the second one back here, make sure that it's in. Yep. And we'll adjust the antenna coil on the back here now. We had this at 12 o'clock. That's why it's taking such an adjustment. So I need to recheck that again. So I'll move that, and then I'll try and adjust this for a peak. Yeah, that's at its peak there. So then I'll recheck this one here because I moved that. This is what happens when you move the antenna coil. You have to remember, or the antenna compensator, you got to remember to bring it back, or the antenna coil adjustments. This only affects the bottom two portions of the band. So that was it. So there we go. So that's okay. So the rest of the bands don't have it. It's just these two for the two bottom bands is the only two in the back. You got to remember to have this at 12 o'clock, or you'll not have this centered. So there we go. Now, what I'm going to do is go back to the 3 megahertz part, 3 megahertz, and we'll check the upper end of the band and see if it's still on. I see it's a little bit out again, so we need to go back and do that. And that's where these things get fun to tune. You see, because you got to go back and forth until it puts it into alignment. Should be holding this up a little bit. And that's this one here, and then we'll go back and peak this one here. There's none for the antenna, this is just for the other stage, for the RF stage. And there it is. So now we'll go back to 1.4 again and check and see if it's on alignment. 1.4, 1.4, there we go. So now we know that we have our band aligned, and that's how you align one of the bands, and they're all like that. So there is a couple of tricks though to this, and when you get into the higher bands, when you get into like the 18 to 31 megahertz band, there's a lot of coupling between the RF stage and the actual oscillator stage. So you'll tune the RF stage and it'll drag the frequency off. So what you do is you pre-tune this until you find, you know, the frequency and align the band, bottom end of the band and then top end of the band for the 18 to 31 megahertz. And then, you know, tune for a peak here until you get some sensitivity. Disconnect your antenna at this point, so it's aligned, so your band is aligned to your signal generator. Disconnect your antenna, go to the bottom end of the band, and tune this until you get maximum, absolute maximum static, okay? So tune that for maximum static, and then go back, because it's going to pull the alignment off, and then go through again and align this again, and then go to the top of the band and tune this one in, obviously again to realign the top of the band. And then once it's the top and bottom are aligned again, go to this trimmer and tune it again. Disconnect the antenna from your signal generator, or your signal generator from the antenna jack, and tune this one for maximum static. Then go to the bottom end of the band and tune this for maximum static, and go to the top, and then they should balance out. And once you find maximum static on both of these, then put your signal generator back on here again and align these, and you should be right on the spot, okay? That's a little bit of a trick with these things. And another thing is you'll hear image frequencies with this one when you tune this one. So you'll tune it and you'll come across it and it'll go doo, and you'll turn it a little more, it'll go doo, and you're like, what the heck? It's doing it in 2 spots. How can it do that? Well, that's imaging. It has a bunch of images on here. So what you do is you usually tune the stronger image. And I found in this radio that the stronger image is usually closer when the slug is closer to the bottom of the coil. So you can wind this in quite a ways, and then the first tone you hear when you're tuning it in is when you're on frequency. The second one will be a little bit weaker. So you want to do that. If you don't do that, your band will be weak. So it'll take a little bit of fiddling around, and what I usually do is, because there's so much, they call it interlock between the two on these upper bands, what I do is I start with the bottom end of the band first. So I'll align the bottom end of the band, and then I'll move right up to the top end of the band here, and then I'll work my way up to the 18 to 31 position. So this is the bottom end here. All right, this is the second band up, and then you go the third, fourth, fifth, and then sixth, and that's kind of the way you want to do it. Work your way up and work your way closer to the top band, because this one here is very sensitive to anything. And when you put the bottom lid back on this radio, it will shift that band just a little bit. Not too much, but you'll hear it. If you have a BFO node on, or if you're listening to a frequency, say around 28 megahertz, and you put the bottom cover on, it'll go whoosh, right off frequency. But it won't be that far. So it'll be just a little bit. And that's just the nature of the beast. That's the way that these guys are. But once you get the thing fully aligned, you'll find out that it's a, pretty darn good receiver. And it's actually really fun to operate too. So that, in a nutshell, is how you pre-align these, or align them. Make sure yours is in the case. Mine isn't in the case, so you want the black case on your radio first, because when you put the case on, it might twist or contort the chassis, and that will cause frequency drift. So any kind of torsion on this at all, like when even pushing your finger on it, will cause that 18 to 31 megahertz band to move. Even putting my hand close to it like this, you can play it like a theremin. It's that incredibly sensitive. So you want to have it in its black case. You can't do this with the bottom on, so you have to have the bottom on. The only two antenna adjustments are the bottom ones. The rest are fixed for the other bands. And as I say, just go through and do that with all of these. Remember the maximum static thing though, because that is really crucial in getting these things to maximum sensitivity on the upper bands. The lower bands aren't so particular for that, but the upper bands really rely on that tuning procedure. So as I say, align the oscillator first, make sure that it's on the frequency, that your band is aligned like what we did on all the bands, and then go back to the upper band, and then go to the lower part of the band where the alignment is, and tune this for maximum static. And then, as I say, go to the upper part of the band, the highest frequency, you're supposed to align it, and then tune this one for maximum static. Of course, this is for one band, and this is for another band, and then this one's for another band. So that's how they all work. And then after that, you'll be dealing with a pretty decent receiver. There you go. Hope this helps. Here's a quick example of how well the noise limiter circuit works inside this Hammarlund HQ-120X. So this is with no noise limiter on, and this is the circuit with the 6Z7 in it. Alright, I've subbed mine with the 6N7. It's a direct plug-in and it's a shielded tube. Okay, so I'll turn the noise limiter on here. And that's with the noise limiter on. You can hear in the speaker here how nice and mellow that is now. And I'll reach over here again and turn it back off. You can see on the scope what a dramatic difference that is. That's with it back on again. So that's a pretty impressive noise limiter, and it really doesn't affect the intelligibility of anybody's speech or anything. You almost don't even know the limiter's on when you're listening to a radio station. So it does work very, very well. Well, this Hammarlund HQ-120 radio project is finally coming to an end, and quite the restoration project it's been, as you've seen in the video. But, well, worth it. You know, it really is quite a handsome looking radio, I think. So that pile of rubble you see in the corner is all the parts and pieces that are out of this radio. There's lots of stuff that ended up on the floor, and some stuff that's not in the pile, like the speaker and the line cord and stuff. But, you know, that's pretty much the gist of what came out of it. It really is quite the performer now that it's aligned and completely rebuilt, and what we're going to do is head into the shortwave bands and the broadcast band and check out how well it actually works. Here we are at the bottom end of the broadcast band, and it's the night time here, so that means that we have conditions. Now if you remember what we talked about in the beginning of the video, how when conditions are happening, it's kind of like that rock skipping on the water, or the signals, you know, going up to the atmosphere and then bouncing back down and coming down in different parts of the world. Well, it's doing that on the broadcast band right now, and I have signals coming in from all over North America on the broadcast band. So right now we're at 0.54 megacycles, or 540 kilocycles, and we'll coast through the band with the main tuning. We'll leave the band spread alone because that's fine tuning for a lot of the other bands, but not for the broadcast band. It really doesn't do anything for that band. So we'll leave that at 200, and we'll just play with the main tuning, and I'll just quickly coast through the band and give you an idea of how many signals there really are coming in right now. And this receiver is pretty sensitive to all of them, so it's listening to lots of signals from all over the place right now. So I'll turn up the audio gain.
Particularly shocking, given reports that girls, possibly
and I'll coast to the band.
May have been forced to...
Cutting-edge reports from those in the true epicenter of the conflict, the people.
Within 3 days, as promised. We even brought James Taylor.
But he still has to send it to you. I would think that would be... That's
Something on his mind. Fish and chips. This smash hit comedy is...
Personnel saw a vehicle flee on a public road outside the area's perimeter.
866. Audio coming up. Calls and comments.
consultation. As an NBA Hall of Famer, I appreciate professionals who perform.
So,
Do you think that you would have gotten into the
ESPN analyst Tom Waddle.
7:30 traffic hotspots.
The Patriots are probably one of
and you can take a tour of it.
jug of DEF to your truck? Well, Pilot Flying J
Pictures and messages.
We will send them going into your home. Through you, and that gives you all that you need to take those steps toward what he is saying to do.
So you can see, I'll just stop here on the band, you can see how many frequencies there are, and it just keeps going and going and going as we roll up the band. Right now we're about, we're only at 0.82, so that's 820 kilocycles right now, or 0.82 megacycles, however you want to look at that. So we're really still low on the band. We have, a lot of broadcast band to go through yet, and there's just so many stations. So if you have a receiver like this, you can just, late at night, you can slowly coast the band, and you can, really look for that bizarre radio station DX. Sometimes you even find pirate stations in here, that stations that aren't supposed to be on here that really are. So there's a lot of conditions in right now on the lower bands. The upper shortwave bands right now aren't active whatsoever. They come active in, certain different parts of the day. They're the odd strong frequency every now and then, but for the most part, the upper bands really aren't all that active. So what I'll do is during the daytime, I'll come back and I'll let you hear the broadcast band again, and you get to hear how clean it is because there'll be none of these conditions going on. It'll just all be local stations, and we'll listen to some of the local stations, and we'll also cruise some of the shortwave bands at that time, as I say, because they're just not active right now. We're just going to hear static. So all the different bands, they come alive in different parts of the day. The later the night, usually the lower the band. And right now the broadcast band and the 160 meter band would be the ones that would be active. Here we are on the broadcast band during the daytime. So there's not so much skip or conditions coming in, so we can focus a little more on some of the more local radio stations. So keep in mind now, I don't know if I mentioned this before, but when these radios warm up, you might notice that the dial might not be right on the marker. It might be on either side of the marker, and that's quite normal because these radios, they really go from stone cold to easy bake oven. And I usually align these about 45 minutes into their warm-up cycle. That's about a happy medium. So usually they're on, either one side when you're aligning them and they move to the other side, or vice versa. And that really depends on the radio you're aligning and how the radio, when you're aligning it, how it feels. And you can really watch how it responds to your alignment after a certain warm-up cycle. So sometimes, people will align them a little bit before the dial marker so that they kind of come on when they're warm. And sometimes when they get really hot, they'll go just a little bit over the dial marker. And what I've done with this one is I found kind of the happy medium so that it's usually within the dial marker, just a little bit of either side. And that is really quite normal for all of these particular receivers. You got to remember, there are no crystal controlled oscillators or PLLs or anything inside of this radio. This radio is all free running oscillators inside, and as I say, it goes from just about room temperature to really, really hot because the lid on the top of this radio stays closed. There's very little ventilation on it, and this really is a coffee warmer. This radio, you could put a cup of coffee on top of it, and it would keep it warm. This radio really does get quite hot. I can feel the heat coming off the face of the radio already, and it's been on for about an hour and a half right now. So that's absolutely normal with these radios for them to move around like that. So if you perform an alignment, chances are you've done your job right. It's just the radio. That's the way that they operate. They move around a little bit. So what I'm going to do now is I'll tune around on the AM broadcast band and we'll listen to some of the more local radio stations and get an idea of the quality of the sound. Here we go.
In the world, sang in presidential inaugurations and even Olympic ceremonies.
Killing us!
In Atlanta, Dr. King's daughter Bernice invoked recent police killings, saying many have been gunned down.
He did in the Book of Acts.
I want
So you can get an idea of the sound quality there.
Welcome back to the 180 on CBC Radio 1. I'm Jim Brown. Celebrating it when it's all said and done.
Man, it was
Traveling for the Pacific Highway, also a 45-minute wait, so busy. Pick your poison. Both of them are about 40.
But the names will stay the same.
All right, how about this? Directors Adelphia. It's classic.
I love your enthusiasm, but...
Would you rather be healthy, energetic, and fit? Join us on TexasSuperfood.com or call us at 844... True source of our value from her conference on self-worth.
So this radio station right here that you're listening to is about 300 in miles wise away. So about 300 miles, I guess that would probably be driving wise anyways. So that's pretty good for the daytime when there really is no conditions. And you hear the fluttering that's underneath that radio station. The fluttering is another radio station competing with this radio station for this frequency. So you can imagine how far away the other radio station is.
7669. Enrollment is open year.
Bailey, as I said, new appliances, expert advice. Plenty of options make choosing the right appliances much easier.
about 20 to 30, depending on what they are, so.
Baseball notice, Max Scherzer heading to Washington. 7-year deal with the Nationals worth
210 million.
This is just drapes matching drapes. That's just somebody not having enough color palettes.
Hey, it's tan, and downtown it's tan as well. Use 1130 time, 233. I'm Doug Brown, the Broncos.
What the nickel's all about, so here he is.
Sounds like conditions might be changing. That's a pretty far away station. Sounds like it could be coming from Mexico or something like that. So conditions are already moving around, and it's only midday here. But that gives you an idea of the sound quality and the sensitivity. Now, this receiver right now is hooked up to an 80 meter inverted V, so the antenna is completely non-resonant on this broadcast band right now. So that gives you an idea with just a random wire of how well this radio really does work. So what we'll do when I come back is we'll head to the shortwave bands, and we'll look at some of the really high bands, say the 10 meter band and around there, and see how it receives up there. That's where these radios were known to not be too incredibly sensitive. So let's see how sensitive this radio really is on those bands. Here we are on the upper shortwave bands. So this is just underneath the 10 meter band, and this is called the 11 meter band, which is the Citizens band, and a lot of ham operators use this particular band in order to see if the upper bands are open. It's pretty active, so this is where this is really at the top end of this receiver. So let's see how sensitive it is on an 80 meter wire. There's no 11 or 10 meter antenna hooked up to this. This is just really looking like a random wire at this frequency right now, or at these frequencies. So let's check out the sensitivity. Peek up the tuning here.
Get your pickup load of it if you want it.
I use this for fine tuning up here. Just rock it a little bit.
Yeah, if you have 4, 5, 6 people, you need a pickup load of it, Cody. When you cook it down, there ain't nothing left.
So that's one frequency that's active in the on the CB. It's a really small window on the dial here where it's actually active. Just cruise in here and see if I can find any big signals. There it is. There's some big signals there. They're all on top of each other. They're all talking at the same time, so chances are they're trying to talk to the same person. Somebody that's obviously pretty far away. You can hear some of them are pretty strong in there. You can tell that they're probably running some form of power on the 11 meter bands. You can tell by the sound of his carrier, he's pretty compressed. So there's probably some sort of heavily driven amplifier, should we say, in there. This is the 10 meter band. I think it's pretty quiet right now. The 10 meter band really starts around 28 megahertz. There's a bit of CW. I think that's a beacon again. So it's a little bit of a beacon. I can hear some other CW in there too. You can change the beat note by moving the beat oscillator around. Now you have to keep in mind that also when you take this off of AVC and put it to BFO or manual, you have no S-meter action anymore. It shuts the S-meter off. So when you're listening to sideband or to any sort of CW note on the BFO, you won't hear or you won't see any S-meter action at all. It'll just rest down at the bottom. That's normal for these receivers. You can hear how nice and stable that is. The receiver's really stable up on these bands. At least when it's rebuilt, they are. You can sit and listen for, listen to a single sideband transmission for a long period of time without having to readjust. Once they're warm, they work very well. But you have to let them warm up. That's very important. Oh, lots of people talking at the same time down here. Lots of compression going on in there. Man, that's crunchy. Be nice to find a cleaner transmission. That's a bit cleaner. So anyways, you get the idea.
The red beads, and I put them in a bowl, and I crumbled up cornbread in there, stir that up, chop me up some onions, throw that in there, chop me up a little bit of jalapeno peppers in there, and then pour hot bacon grease over the top of that.
Yikes, that doesn't sound too healthy. Anyways, we'll head on down to the 15 meter band and check out the 15 meter band. See what we can hear down here. Oh, I went too far. That's the this is the WWV, sorry, on 20 megahertz. So that's the international time signal, or just the time signal. Hear how nice and strong that is. So when these are tuned well, that gives you a really good idea of, the signal strength on the upper bands. They do really work quite well. So anyways, I think that's a pretty good example of all the bands anyways. I could keep tuning through the bands here forever and listening to broadcasts and stuff, but this is, I think probably, I'm not sure how long this video is going to end up being. I think I've got probably 5 or 6 hours of footage I have to sort through here. But I really hope you enjoyed, and I hope this gives you some insight into the way one of these old radios really does work. And they are really a pleasure to operate when they're working properly. They're really fun to cruise the band late at night and find all of those hidden little frequencies and things like that. I have a neat little thing that I'm adding to this radio, and I will do another video on it, and it'll really help you find all the little hiding frequencies, the ones that you can't even hear, you'll see. And that will be the next video. So I hope you enjoyed this, and if you did, give it a thumbs up and stay tuned, and I'll have some more of this crazy stuff coming up probably quite shortly. Alright, bye for now.